Good morning, good afternoon, good evening. I'm Frédéric Padilla from the Focused Ultrasound Foundation. And on behalf of the FUS Foundation and the AIUM, and on behalf of the organizing committee, we are very pleased to welcome you to this first session of our workshop series. We have more than 200 registered participants so far, so we are expecting very exciting and stimulating discussions. So a few words about the context of the workshop. This is part of an ongoing collaborative effort between the American Institute of Ultrasound in Medicine and the FUS Foundation to develop and promote the use of therapeutic ultrasound. This has materialized already in the form of webinars and more to come, and today this first jointly organized workshop. So our aim in organizing this workshop was to really review the state of the art of cavitation in therapeutic ultrasound and more generally bubble activity. So I'm sure you noticed that we intentionally avoid the use of cavitation in the title of the workshop, and this may be an important semantic question that I'm sure we'll have time to address in the sessions, as we realize that cavitation for the physicist and the physician may convey different meanings. So the aim is to identify level of knowledge, gaps in knowledge, best practices, and the overall objective will be to propose guidelines on how to best detect, monitor, map, and quantify cavitation and bubble activities for ultrasound therapy. And so now Brian will say a few words.
So welcome, everyone. So in terms of the workshop organization, this is organized as 6 sessions that span September 24 to 29. They'll occur every Friday from 10 a.m. to 1 p.m. Eastern Time in the U.S. It's composed of 5 technical sessions covering the topics that you see listed on the screen here. The last workshop session will be an effort to summarize what we learned over the course of time, how and what to measure and report, and then to look forward to the next steps that we might take in pursuing the objectives of the workshop. I have the pleasure of doing the acknowledgments for this. First of all, our support from the FUS Foundation and the AIUM Future Fund. We want to thank Emily Whipple at the FUS Foundation and all the people managing the logistics and organization for the workshops over the next few weeks. We want to thank the organizing committee. They worked diligently and spent several hours in conference calls determining the composition of the workshop and how the logistics would work for the presentations that you'll see over the next few weeks. And then we want to especially thank the list of speakers who volunteered to participate, along with the panelists who will be leading the discussions of these topics in the coming time that we share together. Now back to Fred for some logistics.
So you are all connected to the platform. So I'm sure you found the access to the live sessions. You saw that on the left side of the main page, you have access to suggested readings, references. You can access the list of participants on your own. Profile page, you can update your biography, your photo, your social media information, and you can connect through the platform if you want with other participants, sending message that might be useful given that the workshop will be over several weeks. In terms of organization of the sessions, so they will be organized. The first part of the sessions will be talks, pre-recorded talks, each of them followed by 5 minutes of Q&A. We'll have a short break and we'll resume the session with a panel discussion with all the speakers and invited panelists. So we encourage you to participate. So you can submit questions through the Q&A on the web page of the workshop. You can submit the Q&A as the talks are given and during the panel discussion. This is for the first 5 sessions, and the last session will be in the form of open Zoom meeting where everybody is expected to contribute. The sessions will be recorded and should be available in the event platform by the following Tuesday, so next Tuesday for this session. And so now it's my pleasure to introduce the first session, so cavitation detection equipment, that will be moderated by Professor Kostas Avanatis from Georgia Tech and Professor Konstantin Poussios from the University of Oxford, and they will give you a few words of introduction.
Thank you very much, Frederic. I'm Konstantin, I'm Director of the Institute of Biomedical Engineering at the University of Oxford. I'd like to start by thanking Brian, Frederic, and Emily for bringing us together for this very exciting series of expert cavitation seminars. I would like to start by introducing my co-moderator, Professor Kostas Avanatis from the Georgia Institute of Technology, who has worked extensively around the world and most recently at Harvard and before that at Oxford on several applications of cavitation-enhanced drug delivery, particularly in the brain. And I'm also delighted to call myself one of his postdoctoral mentors. So very pleased to be doing this alongside him today.
Thank you for the kind introduction, Konstantin.
We have done with the organizing committee and tried to achieve with this first session is a first introduction on the technology and the equipment that is used for the word that shall not be named, cavitation, the one we have tried very hard not to use in all of our advertising literature. And really, this morning will be taken by a list of expert speakers on an expert journey of the signal acquisition path from transducer all the way through to quantifying some of these signals that are relating to bubble activity in the body. So the extraordinary array of speakers this morning starts with Kyle Morrison, who's the president of Sonic Concepts. And I'm almost certain there will be no one listening in who doesn't hold or hasn't held a transducer that has been manufactured or touched by Kyle. He's one of the most prolific contributors to ultrasound technology in our research area, and we're absolutely delighted he's agreed to join us. Immediately following this, we'll be hearing from Professor Kevin Hayworth at the University of Cincinnati, who has been working now for over 10 years on novel methods of cavitation detection and cavitation imaging. And with Kyle having focused on sensors, Kevin will actually focus on the signal processing of these passively received signals that are commonly used on passive cavitation detectors. We will then move to Dr. Michael Gray, Senior Research Fellow at the University of Oxford, someone I have the pleasure of working with very, very closely, who came in the opposite direction from Georgia Tech to Oxford in order to complete some of the early clinical studies that involved drug delivery and also cavitation detection in patients. And Mike will primarily focus on the calibration issues that surround these cavitation detectors or these methods of cavitation detection and some of the challenges we encounter in making comparable measurements across laboratories and across applications. From there, we will move to Professor Nathan McDonald from Brigham and Women's Hospital at Harvard. Nathan has worked more than anyone I know on developing novel hardware to enable delivery of ultrasound, but also detection of cavitation through the skull, and will therefore primarily focus on transcranial hardware. And then we will hear from Professor Elisa Konofagu at Columbia for her pioneering work on using single-element passive cavitation detection, both preclinically and clinically, in order to achieve a blood-brain barrier opening. And last but not least, we will hear from Itai Rachmilovic, who is the Neuro Applications Manager for Insightec. Insightec was arguably the very first therapeutic ultrasound company to integrate passive cavitation detection within a commercial and clinically approved system. And we very much hope that Itai will be able to share with us their unique journey in not only integrating, but also utilizing and gaining approval for this type of technology. So without further ado, I would like to welcome you all to the workshop and invite the very first speaker, Kyle Morrison from Sonic Concepts, to deliver his lecture.
Hi, I'm Kyle Morrison, president of Sonic Concepts. I wanted to present an overview on passive cavitation detectors and the design and calibration methods we use at Sonic Concepts. I wanted to thank Kostas and Konstantin for allowing me to present on this topic, and to the Foundation and AIUM for organizing this workshop. So, cavitation events. What is passive cavitation? They're low amplitude acoustic emissions from bubble events. So there's a range of cavitation types, from stable cavitation, which emit super and subharmonic content of a bubble's resonant frequency, and inertial cavitation, which is actually the collapse of those bubbles, and they actually emit these high frequency content. So really the solution is to have a highly sensitive and wide passband passive receiver sensor, which we're calling passive cavitation detectors. So here's a general illustration of an ultrasound transducer emitting sound to an intended focal site. And there's a PCD receiver that's transverse, looking in perpendicular. And so here's a PCD, and then the PCD and often needs filtering, which we're using notch filters to dampen out the transmit fundamental and harmonic frequency content of that focused ultrasound transducer. And then the filter goes, the line goes into an oscilloscope where you detect the waveform, provide an FFT to get the amplitude and frequency content of those events. So here's two illustrations. On the left side is another example of a transverse PCD looking into the bubble site of interest. This would be in a bench, and on the right hand side there is actually a Y102, our cylindrically curved PCD, and so it has some focal gain, which we'll talk about later. On the right hand side is a coaxial PCD, so it's actually spherically focused with the same radius as the transducer, the HIFU transducer, and it's intended to overlap with that focal site. And it can be used for minimally invasive applications or non-invasive applications. So how does this work? You have your focused ultrasound one-way transmit. So, you take your speed of sound, your radius of curvature to find the time of flight for which that event occurs. So in this case, we're 63 millimeters into 1481 meters per second sound velocity of the water. So we're about 43 microseconds. So the PCD will actually detect the two-way response. So you want to double that. So we're looking for an event occurring around 85 microseconds. Here's a couple other examples. On the left-hand side is a replaceable miniature PCD within a HIFU transducer. And then on the right-hand side, we make ring PCDs with a HIFU transducer that actually will accept an imaging probe. So you have passive cavitation detection, imaging for real-time guidance and monitoring of the HIFU bubble events and cavitation. All right, so we have different kinds of PCDs. Let's talk about the wide passband version. This is a 10 megahertz PVDF piezo polymer material that I'm going to be discussing. It's has a low Q. Its goal is to have a reasonably high sensitivity over a large bandwidth. And then we really want a low density material, which this is, with a low longitudinal impedance, which lowers the Q, and then high losses, which lower the Q. And then in combination with the piezoelectric layer, we use front matching layers and rear acoustic loading materials used to optimize the sensitivity over the bandwidth. So here's an example of a received transfer function. Notice that from 0 to 10 megahertz, we're within 6 dB. And so we're at 17.5 millimeter diameter. That's a lot of aperture. So we're able to get about 38 volts per megapascal, 31.6 dB volts per megapascal. To compare that with a 200 micron needle hydrofoam, this is 3,000 times more sensitive, or 70 dB more sensitive. So this really helps with SNR, and really we become less reliant on a preamplifier. So this is 110 micron thick piezopolymer material that we're using here. So look what happens when we go out to 20 megahertz. So it starts to fall off pretty rapidly using 110. So it worked up until 10 megahertz, but it falls off too much out to 20. So what we do is we reduce the thickness of that piezopolymer by half to 55. You lose about 6 dB or half amplitude but the bandwidth is there, so within 6 dB. Here's an example of PCD sensitivity with focusing. So to give you an example, an unfocused sensor will reach its transition plane at 2D over 4 lambda. The diffraction patterns up until the transition plane will vary in phase between an amplitude of 0 to 1, where 1 is the amplitude at the surface. When focusing an aperture, we increase the focal gain, which you're seeing in blue, which forces the field of which it's sensing to begin diverging at the acoustic maximum. So in this case, when expecting emissions around 2 megahertz, using a spherically formed concave surface with a 63 millimeter radius, we actually increase the sensitivity by a factor of 6. So 38 times 6, we're at 228 volts per megapascal. So that's extremely high at 2 megahertz. But what happens in the presence of subharmonic bubble emissions using that same sensor? Here's an example comparing unfocused versus focusing at 250 kilohertz. The benefits of focusing are lost and around the site of cavitation. The sensitivity is actually approximately 44. So you lose a bit of sensitivity just because of that focal gain reduction. This plot superimposes 4 frequencies. So we're ranging from 250 kilohertz to 2 megahertz to illustrate the dependence on frequency using a focused aperture. So focused PCDs are very difficult to calibrate within a reasonable uncertainty. This spatial resolution across the frequency spectrum is very difficult to quantify. Normally a needle hydrophone, for context, is calibrated at a point in the far field since the spatial resolution isn't an issue. The focused PCD geometric focus cannot be assumed to be in phase in this case. So it is possible to attempt calibration of the geometric focus and disregard the phasing variability, but this is normally a service Sonic Concepts doesn't provide. Instead, we rely on electrical impedance and the axial focusing simulation to approximate the sensitivity. So let's go back to the 10 megahertz PVDF case and look how it performs as a two-way pulse echo sensor. So again, notice we're at 31.6 dB volts per megapascal. Well, as a pulse echo two-way response, it's only 15 millivolts per volt. So we have reasonable bandwidth, but poor sensitivity. So let's look at the transfer function, 1 kilopascal per volt. So it's just not a good transmitter using piezopolymer. So what we need to do is, as a pulse echo transducer, get away from piezopolymer and start looking at ways in which to improve the sensitivity and for transfer function. So looking at 1,3 composite, we increase the density by 4 times. We increase the dielectric constant by 185 times. So that means we can drive this a lot harder than a piezopolymer, and we decrease the losses. So here's an example of the transmit transfer function. So notice we're at 18. So we're about 18 times more efficient than the piezopolymer design, and it can handle about 200 times the voltage. So we're using a resonance thickness here on the composite, a quarter wavelength matching layer, and the same rear acoustic loading that we were using for the piezopolymer. So we have good bandwidth for the pulse echo now. We're 12 times the sensitivity as piezopolymer with reasonable bandwidth. But here, just as an example, let's just go back and say, okay, we want to use this 1.3 piezo composite as a receiver. Just to prove the point, we reduce the Q, or because of its high Q, we reduce the bandwidth quite a bit, and we actually lose 5 dB of sensitivity. So just an example of why we want to trade off different materials for different types of sensors. Just to finish, we have a couple other designs that are not ultrasound guided and integrated with Focused Ultrasound. On the bottom left is a two-way side-looking PVDF sensor that you can actually put near and have an invasive probe. And on the top there is a ring PCD. So if you're looking for cavitation events, you can put this ring PCD around the site of interest. And the smaller PCD you get, the less signal to noise ratio you have, the less sensitivity. So we do provide preamplifiers with 20 dB gain over a wide passband up to 50 megahertz. And these can be made MR compatible if necessary. So thank you for your time, and please contact me with any questions, and I'm happy to take any questions. Thank you.
Hi, Kyle. Thank you. Thank you so much for the insightful presentations with respect to design and the calibration methods on passive cavitation detection. So we'd like to start this brief discussion with some questions that have already been posted on the chat. And the first question is, how is the directional sensitivity of passive cavitation detectors is affected by the aperture? And this mostly is a quick question with respect to the first designs that you presented.
So can you repeat the first part of that question?
How is the directional sensitivity of passive cavitation detection affected by aperture? And really speaking in reference to the early PCD you discussed with aperture of 17 millimeters.
Yeah, well, okay. So the larger the aperture, the smaller the directivity becomes. And so, it's a trade-off. If you're looking for more directivity, so you're looking for a wider field of view, the smaller sensor you want in order to accomplish that. But in turn, you do lose that sensitivity and you lose that overall signal to noise ratio that you would benefit from the high sensitivity of a higher element. So it's a trade-off there between sensitivity and signal to noise versus directivity. But the smaller, of course, the element, just like a needle hydrophone, the smaller the element size, the more directivity you have.
I really am quite intrigued by your data that show that the amplitude and spatial profile of the passive cavitation detectors is very sensitive to frequency. And for passive cavitation detection, you're very well aware of that. We are interested in picking up different spectral components of the emitted bandwidth from the microbubble. So how do you think this can affect attempts that will try to quantify the acoustic emissions, for example?
Based off of the frequency content as a function of focal gain throughout the axial. Yeah, no, that is a real problem. And so you really need to appreciate the dependence of frequency, based off of the spectral content. Just because it's curved, you're gonna lose pressure gain. And so, yeah, it is important to have that information. Also, you have those near fields before it transitions over to the far field. You have those near field events, and that can give you false positives or true negatives, or it gives you some uncertainty there. So it is that is a hurdle that we have right now, and something that we would be open to with suggestions on how to understand that more.
Yeah, and then there is a follow-up question, I guess, from one of the attendees that say, like, is there any design that we can we have a specific design for the passive cavitation detection when we are interested in detecting stable or inertial cavitation, essentially harmonics, ultraharmonics versus broadband emissions? Do you feel like there are any way to attune, I guess, the system?
Yeah, I mean, if you want to narrow down the frequency range, you would start to look at, using a higher Q sensor like composite or ceramic in order to benefit from the sensitivity and signal to noise of that base. So, I mean, you can use a piezo polymer. It's just not going to be as sensitive. You could use matching to match a certain source impedance of your preamplifier. There's tricks to be had there. It just really depends on the frequency range and the directivity in which you really want to focus on.
Go ahead, Konstantin.
Perhaps a question from me, first of all, to thank you for joining us, but I believe must be quite an ungodly hour in Seattle to be doing any kind of public speaking. And then to ask you about the directivity or the sensitive area of, you talked about the finite aperture transducer versus the point receiver. What can you tell us about these ring transducers? Do you get to hear everything that is inside the circle, or is it slightly more subtle than that?
Yeah, no, again, you have that focal gain characteristic. And so that's the optimal focusing scenario. You have a full ring. And so, yeah, it would be beneficial to really apodize that ring if you really want to quantify the full cross-sectional area of it, so you can almost steer it and apodize it and figure out where that content is. Having a full ring, just one single receive, you're really just looking at the central axis and the cavitation regime there. It's highly focused. You're not going to really see much away from that axial focus. So you really want to mechanically get that centered relative to your site of interest.
Thank you, Kyle.
And Kyle, do you feel that there are any major differences when, for example, we want to have a single passive cavitation detection versus building an array of elements? Do you feel that what are the design considerations that somebody has to take into account when trying to decide which one of the two methods to employ?
Well, yeah, so just comparing a single element versus a multi-element array, it gives you the same benefits as using a transmitter with multiple elements. You're able to narrow in on where that treatment site is. If you're wanting to look for bubbles around the cloud and content, you can then steer it and get a good signal to noise ratio and localized monitoring that way. So there's definitely benefits to having a multi-channel PCD arrangement.
But I guess the caveat here is that you need to have much more complex system, right?
Yeah, you need a multi-channel system. You need to make sure you properly place all the elements, and then it's same issues with focusing the aperture. It's frequency dependent. So if you want to have this monitoring steering range of your PCDs, that's not only spatial but temporal. You have to, if you wanted to calibrate that and really take advantage of that system, you need to do it based off of the frequency range as well. So that's very complex.
Okay. Okay, I'll keep that then. So it's a challenging problem that needs to be addressed. And here I would like to thank you thank you once again for sharing your insights on passive cavitation detector. I'd like to ask you to stay here for our panel discussion at the end of this day. And I would like to move to the next presentation.
Thank you.
I'd like to thank the organizers for this session and everyone participating in this workshop. For my contribution to it, I'd like to talk about receiving and processing passive signals, which may be used in cavitation detection. First, I'd like to just briefly disclose my research funding support. When we passively receive cavitation emissions, there's a fairly standard setup that's used by many groups, and although the details will vary from group to group and experiment to experiment, the main idea is that a therapy transducer will be used to cause cavitation-mediated bioeffects. The passively received emissions coming from that are detected by a passive cavitation detector, and then the signal may be amplified with a preamplifier, resulting in an analog signal that's shown here as X as a function of T. Data acquisition boards are then used to digitize those signals, put them onto a computer, where they may be processed to produce things such as a power spectrum as shown right here. Now, the choice of a passive cavitation detector can be designed to be sensitive over a relatively large area by using an unfocused transducer, or over a relatively small area with a focused transducer, and the application being the thing that dictates which of these we would select. Now, the choice of the transducer, preamplifier, and data acquisition tool should be designed with the bandwidth of interest in mind. In addition, it may be possible to use an inline analog filter to further assist in this. Now, care should be taken when determining what to use for these, in particular, whether or not we want to include the fundamental intonation frequency within that bandwidth, which can be a very large signal that can affect the signal-to-noise ratio of other frequencies that are much smaller, such as our ultraharmonics or inharmonic or broadband emissions. The choice of the instrumentation can be adjusted to both maximize the signal recorded, while also adjusting to improve the noise floor for the situation at hand. In this particular power spectrum example, we can see that the hardware is created to have a relatively flat response between approximately 1.5 and 3.5 megahertz, but then the sensitivity drops off pretty dramatically outside of these regions. It's also important to keep in mind that in our theory and calculations, we often assume that we're working with either a continuous time or a continuous frequency signal, but in reality, our data is discretized. We need to be careful to take into account the effects of discretization because it's not just magic. And in fact, if we look at the relationship between a continuous Fourier transform and a discrete Fourier transform, such as might be commonly implemented on MATLAB, there are scaling factors that involve the sampling frequency. There's also phasors that involve the frequency step size that are present. Now, even if we take those into account and we plot our magnitude of the Fourier fast Fourier transform or our discrete Fourier transform to get something like a power spectrum, we need to keep in mind that this is really only good if we want to compare frequencies within this particular spectra that we're looking at. However, if we want to compare signals from different experimental setups or from different labs, then we really need to move to calibrated systems that might report things in terms of energy or energy spectral density. And when this is the case, we now need to take into things like such as the surface area of the received transducer, physical constants that are in place, in addition to discretization factors, and then also calibration factors that convert from volts to pascals or something similar. Both Collinall and Rich and Mast have provided different pulse echo and pitch catch approaches to obtaining these calibration factors. The core effect, though, isn't that it converts us from millivolts squared of received energy into joules of acoustic energy that are incident on the receiver. This is a fairly complex topic, and I'll leave it to our next speaker, Michael Gray, to outline the various considerations in more detail. Now, besides accounting for digitization of the signal and the relative sensitivity of the received electronics, we also need to think about how we can process the signal. On the left, we see a fairly typical received cavitation emission. We have an initial time where we have predominantly electronic noise. We have our cavitation emissions shown in the green shaded region, more electronic noise, and then we may have a zero padded region towards the end of it. If we were to take a simple fast Fourier transform of the signal, we might get a frequency spectrum that looks something like this. We can see harmonics and ultraharmonics present, but we also see in here a very high frequency ringing that's present, and that has to do with the discontinuity that occurs at this location right here between the electronic noise and the zero padding. If we truncate our data so that we don't have any of that zero padding, we can clean up the signal substantially, but we see that we still have a relatively wide bandwidth at our harmonics. And this is due to the fact that Fourier transforms assume a periodicity of our signal, and we still get a discontinuity between here and the beginning of the signal when it assumes that it's periodic. If, however, as we follow the work of Mast et al., and we use an integer number of wavelengths for the size of the window that we're using here, our frequency bands will fall such that our energy can be contained entirely within our harmonics and our ultraharmonics, as is shown in this kind of optimal truncation. Now that works well for long pulses, but with short pulses, it's hard to truncate our signal at an integer number of wavelengths. So an alternate option is to apply windowing to our signal. Here we see 3 different cavitation emissions received at 3 different amplitudes, producing harmonics, ultraharmonics, and then ultraharmonics plus inharmonics. Now this is with no windowing applied, which is equivalent to applying rect windowing, but we can apply other windows such as Hamming windows or Blackman-Harris windows. When doing this, this can significantly clean up some of that high frequency ringing that we observed before, and we see in the Blackman-Harris filtered window on the windowing on the bottom. Unfortunately, however, as we decrease the side lobes here that produce this high frequency ringing, we also increase the width of our main lobe, as is shown here. And in the case of this Blackman-Harris window that's applied to our data, we actually see that the harmonics and the ultraharmonics start to run into each other to the point where we now question our ability to be able to detect broadband emissions very accurately. And so this is a trade-off that we have to play around with as we're looking at our data. In addition to that, we should recognize that these windowing windows also result in a reduction in the energy that's in our signal. And in order to correct for that, we need to multiply by the inverse of the average amplitude of the magnitude of our window, as shown right here. Now, an alternate way to look at our data is through the sum of harmonics model that came from the Oxford group. In the top left from some of their work, they show their received signal. And we have a very large amplitude fundamental that's observed here. If we apply a wideband comb filter, we're able to reduce that fundamental quite significantly, but at the expense of also having reduced the broadband emissions that are located here. On the other hand, if we use a more narrow band comb filter so that we don't affect the broadband emissions as much, we still then end up with a fairly significant signal at that fundamental. So what they did is, instead of just saying we're going to apply some signal processing, they said, why not use the fact that we know that we're dealing with bubbles? And in particular, the emissions that we have from our bubbles could be decomposed into a set of harmonic signals and a set of broadband emission signals that can be modeled as Gaussian data. By fitting a set of harmonics to our original set of data and then subtracting it off, we can be left with just the broadband emissions, and that's what we see in this example here. They were able to retain a majority of the broadband emissions while essentially removing all of the harmonic or the fundamental signal that we're looking at. Besides just looking at frequency filtering, we can also apply other transformations to look at our data. For instance, the Safari group at the University College London used Debouchet's wavelets to transform their data. And they observed that as they adjusted the scaling and translation parameters U and S, they were able to isolate different frequency components. For instance, looking at just the subharmonics, looking at the fundamental frequency, or looking at higher order harmonics in their data. Another alternative that's been pursued by multiple groups, with some of the earliest work coming from the Riverside Research Group, is the application of singular value decomposition. In this approach, a matrix is built by appending RF data vectors to each other, then applying a standard single valular decomposition. The first eigenvector that's observed will often be the fundamental. Then by searching through the remaining eigenvectors, it's possible to find other frequency components such as the subharmonic. Now, when doing this and isolating different components of the signal, as is seen here, they also looked at a comparison between if they look at the subharmonic component just based on a Fourier transform analysis or based on their singular value decomposition analysis. And you see, depending on the number of cycles that's present and some of the other parameters that are chosen, these do not necessarily relate in a one-to-one relationship. The question, of course, remains, though, which of them is more accurate and represents the gold standard truth. Now, the final topic that I'd like to mention in this brief talk is the fact that we also need to deal with our passive cavitation detectors being significantly larger than a wavelength. We typically do this in order to increase the sensitivity of our system. Now, if we have a single bubble creating a nice spherical wave that's being emitted, and we have a nice spherically focused PCD that's located at there, we'll have good coherence of that received signal on the array. However, if we shift this so that the focus of our PCD is no longer at the focus of the source, we'll actually get phase averaging that occurs across this transducer. This, of course, will affect the sensitivity patterns that we're looking at, but more importantly, these sensitivity patterns are now going to be a function of space, which makes things more complicated. Furthermore, we need to recognize that our cavitation source is an ensemble of unknown sources that's going to be dynamically changing in time. As a result of that, depending on the distribution of these sources, the field incident on the receiving element will vary. This is very much analogous to the creation of speckle in a standard ultrasound set of images, and certainly creates some uncertainty to deal with. Rich et al. Proposed that we could potentially deal with this by the inclusion of a diffraction correction factor, which they termed gamma. They defined it as the average total radiated power normalized by the region of interest, which is shown right here as this box here, and indicated by W in this equation, divided by the average received power. In this scenario, we measure the average received power, and we can estimate the region of interest based on the focal volume of the therapeutic insonation transducer. This allows us to rewrite our equation as the total radiated power per unit area is a product of the diffraction correction factor and the received power. Now, under the conditions of wide-sense stationary data and the bubbles being stochastically independent, the diffraction correction factor can be estimated based on the spatial sensitivity of the passive cavitation detector, and that we can estimate from a Rayleigh integral of that passive cavitation detector. When Rich et al. Applied this to some received data, here we see they had both unfocused and focused received data. They were able to model the scatters with the emissions being received by either the focused or the unfocused transducer, and applying those corrections for the diffraction, they were able to see a good correlation between the unfocused and the focused transducers. They were also able to see a good correspondence, as shown in the two bottom plots, between known transmitted powers and received powers that they had. That brings me to the end of this talk, which by necessity can only cover a fraction of what's really been discussed in the literature. Importantly, as we move forward, there are a number of opportunities and challenges for our field. Some of the key ones based on this talk would be that first, we need to develop a uniform approach to reporting our methods with sufficient detail that the work is truly replicable by other groups. Now, this may require the inclusion of supplemental information in our papers, but it should certainly have enough detail on the equipment and their settings, along with the code used for the signal processing. We might model some of this approach on the excellent guidance article provided by Gail Terhar and colleagues back in 2011 for reporting ultrasound exposure conditions for bioeffect studies. A second topic that we'll hear more about in the next talk would include calibrating our hardware, electronics, and our processing. This is a major challenge, and in particular, developing practical methods to do so is very important. Finally, I think a key opportunity that we have in front of us is the development of setups that would allow for gold standard, known valued measurements so that we can compare different approaches. This would allow us to further our understanding of what techniques are best for isolating emissions and testing the assumptions and estimations that go into determining cavitation energy. With that, I thank you for your attention, and I look forward to our discussion.
Thank you, Kevin, for a superb tutorial lecture and covering a huge amount of ground in an implausible 15 minutes. We have several questions from the audience, so let me kick off right away with the first one of those. When you speak about shorter pulses, what are the typical number of cycles that you are considering? So this is something you said early on in your presentation.
Sure, it's a great question, Constantine. I think it depends a lot on obviously the application, right? So we can go anywhere from looking at even just a half a cycle with some of the monopole emission incinerations that we get, and corresponding emissions that we get from intrinsic threshold histotrypsy, right, up through, a lot of drug delivery work has worked with, around tens of cycles, but then getting into even millisecond long pulses. So I think it really depends on the particular application as to how long it's going to be. My experience has been with in defining short. Short would be somewhere in the order of tens of cycles, where you get kind of that transition between having a really nice long pulse where you can do some of that work like Mast et al. Had, versus it getting shorter and you run into some of the issues with, how do you separate ultraharmonics from harmonics, for instance.
Thank you for that. And then, because we have a lot of questions, I'll move through them swiftly. What would be practical gold standard techniques and setups to enable calibration and comparisons of different approaches?
Well, that's a great question, and that's why I threw it out there at the end. I'm hoping through the conversations that we have over the next couple of weeks that we can come up with some ideas for that. Certainly we can do things like which has been done before, scattering off of known objects, known impedances. But I do think it's a challenge and something we need to think about. How do we really replicate something like bubble activity, which is stochastic, dynamic, and changing? I think that's a real challenge. I don't want to pose that or say that I've got the answer for that. I think that's something we need to come up with as a community.
A fantastic thing to talk about further during the panel discussion and in subsequent workshops too. A very specific question on your slide 4, why was there such a large signal for bubbles without ultrasound?
Yeah, so that one I picked in particular that showed that there. So in fact, right, there's no ultrasound. And so all we're measuring at that point is just really the electronic noise associated with our receiving systems. And what that demonstrates, where you saw in that between 1.5 and 3.5 megapascals, what appeared to be a larger signal is really just that the noise floor itself of the system is varying as a function of frequency. And so there's no signal there really, no meaningful signal there. Where it's higher there, we just have more noise.
There are several more questions centering around sort of comparison of these methodologies to determine best practice and identifying a gold standard. I think you've already addressed some of this in your earlier response. There's one here which I'd quite like to give you the opportunity to talk to, which is a lot of the methods you presented require a fair amount of expertise. So for a group that are just users of cavitation detection, is there an open science repository or algorithms, MATLAB scripts, etc., can be shared? Or what can be done in general to enable less expert users to do this correctly, but without significant overhead?
Yeah, so I think we should really be thinking about, where can we put, so from the groups that do have the expertise from this, right, where can we put code repositories so people can just kind of grab those and use them? Obviously, they need to be fairly well documented so that they're used appropriately. So I think that's the number one thing that needs to be done. I think also, though, kind of paired with that is a discussion of, what are, as we go along that receiving pathway, as we have preamplifiers in place and those sort of things, for people to very well characterize in their papers what those, not necessarily characterize, but at least document what those pathways are so that other individuals can use them. I think some of the, kind of more turnkey options like Sonic Concepts is producing will also go a long way towards that, since they can obviously apply their expertise and share that with other groups.
And then I'll ask you a final personal open-ended question. I was delighted to see you talk about, energy and the energy relating to the activity of the bubble. What energy metric or energy metrics, in your view, matter that we should be focusing on? Is it energy? Is it average power? Is it peak power? Do you have a view as to what, if anything, we should be focusing on in that respect?
I think to answer that question, we need to think about what the bioeffect is that we're looking at, right? So if we're trying to do thermal ablation and we're trying to monitor that, right, some sort of time average power is probably going to be something that is most relevant. If on the other hand, we're looking at, drug delivery where, the microbubbles are streaming and we're getting some sort of convective effects, I think, something more along the lines of pulsed average energy, or even a metric of amplitude, so to speak, would be the approach to go with there. So I think it depends on the particular application at hand, and I think that will dictate where we need to be. I think we need to have, and this goes back to having some gold standard measurements too. We need to do a better job of being able to kind of tie these different bioeffects into cavitation and understanding whether or not cavitation is the only metric that we should be using, or if we need kind of a multimodality type method. Obviously your group had a nice paper with Carl Jensen as the first author, where you kind of combine experimental work with modeling work, looking at thermal ablation and trying to develop metrics from there. So I think that's another thing for us to be thinking about, is it doesn't need to be solved with just cavitation.
Fantastic. Kevin, thank you very much indeed. Please stay around for the panel to answer some of these deeper and more open-ended questions. And I'd like to take this opportunity to introduce the next talk by Dr. Mike Ray from the University of Oxford. Many thanks, Kevin.
Hello, everyone, and welcome to this presentation on considerations for calibrated cavitation monitoring. The motivation for this work is the ongoing quest for cavitation monitoring, imaging, and dosimetry methods that offer improved mechanistic understanding of what bubbles do and the relationship of their activity to observed bioeffects. And we'd like all this to happen in an implementation-independent manner. And with this, I mean we want to minimize errors and biases in things that we can control, such as hardware and beamforming, as well as in things that we can't control, such as patient morphology and tissue properties. So in this talk, I'm going to step through a framework for considering these factors, review some of the issues to be mitigated, and highlight some examples of progress. Now, I'd like to run through a framework for considering the factors that influence cavitation monitoring. And I'm illustrating this with a thoracic treatment scenario here, but the concept should apply to any other scenario of interest. But this all starts with an excitation source that launches sound into the tissue, interacts with cavitation nuclei to create a distribution that we're interested in. Now, at this point, the acoustic emissions can go just about anywhere, but we concern ourselves with the paths that go through the tissue to a set of receivers, which themselves are likely to alter the response. We collect this data, process and beamform in some way in order to give us qualitative or quantitative output, which may include detections based on spectrum levels, image formation of the cavitation distribution over some time interval, and using one or both of these to come up with some sort of integrated dose metric. And if it turns out that as a result of this workshop series, we come up with some new dose calculations, I'd like to recommend AppFills as the unit. And before I move on, even though this is a hardware section, I do want to reiterate that, at least for me, proper calibration of the system involves much more than just the hardware. Before I get into a discussion of the technical issues on the left, I do want to talk a little bit about observational limitations, and I'll start here with spatial coverage. So supposing we've got a collection of radiating bubbles. Formally, if we wanted to know the radiated power coming from those bubbles, we need to make measurements on a surface that fully enclosed them. But of course, as a practical matter, that's not going to happen. Certainly, if we start with a PCD, we have an extremely limited view of what's going on. If we switch to a handheld array, for example, it gets a little bit better, but we're still typically dealing with less than 1% of the solid angle. Now, if we move to a ring array, such as used in photoacoustics, or a hemispherical array that's used in transcranial work, the situation is much better. But in all cases, we do still have a limited view of the physical phenomena we're interested in. And this may be especially important if we're worried about dense bubble clouds and effects of shadowing or shielding. The other limitation I want to discuss is that of bandwidth. So here's a pressure waveform from Mitula et al. From a single collapsing bubble. And based on the waveform shape and the time scale, you might expect a spectrum that looks like the black curve in the lower right, where there's over 200 megahertz of usable bandwidth in there. However, as soon as we add in some realities, such as attenuation in tissue or limited bandwidth of a common receiver, we find that most of that bandwidth is lost. Now, I'm not bringing this up so that we can feel disillusioned about what we're trying to do. It's really just to make the point that cavitation imaging, like all other medical imaging modalities, is based on limited observations of the physical phenomena that we're interested in. And so it's on us to make the best use of the data that we can get. And this is where I think calibration can play a major role. Okay, on to the transfer functions. When we think about tissue propagation, an ideal place to start is where we say that the paths between source and receiver are all straight lines, all the wavefronts are spherical, and the media is taken as homogeneous and very often lossless. And these kinds of assumptions do carry into many of the beamformers that are used in cavitation imaging. But of course, those ideal assumptions are not what really happen. Refraction causes the paths to be non-radial and introduces curvature distortion. We can get additional amplitude distortions from diffraction and reflection effects, and we can see significant signal losses due to attenuation. Because attenuation tends to look like a form of low-pass filter, coarser image resolution can result. Receiver response can be broken into two basic pieces. The first of these is electroacoustic response, which is set by construction of the transduction mechanism. Here I've got an example of measurements made on an L74 handheld array, where the bars indicate plus or minus 1 standard deviation across the 128 array elements. And I suppose some lessons learned from making measurements like this is that even though this is a well-made commercially available array, we can expect a pretty good degree of variability from element to element, and we shouldn't expect that the response will be uniform in the advertised response band. The other important effect to keep track of here is diffraction, or if you like, near-field directivity. And this is set by element size, shape, and focusing. To illustrate this, I've got measurements here for two different commercially available arrays, both looking at 4.5 megahertz and a source that's 40 millimeters away off the central axis of the array. Now, the general trend for diffraction is that it lowers the responses at the edges of the array, and clearly the array type has a lot to do with that. So starting with the L74, the linear array, we have about a 6 to 9 dB effect here at 4.5 megahertz. And this may not seem like that much on this scale, but it will in fact change the effective aperture of the array and also impact the energy estimates if you don't tell the beamformer that this is happening. But of course, a much bigger effect is seen with the C5.2, owing to the higher angles of incidence on the array's rotated elements. In fact, the response goes through a null and then recovers into a side lobe, which means that the responses would be inverted. And again, if you don't tell the beamformer this is happening, you'll get some pretty strange responses, not the least of which is you've got a big opportunity here for biasing between measurements of the same exact system, but made with two different arrays. Because this is a near-field effect, if we change depth, we're going to see some changes in these patterns as well. And typically, the further away you get, the smoother these patterns get. But the fact that they're changing for both arrays over these distances, again, is an opportunity for biasing as a function of depth. And this might show up, for example, in the difference between monitoring proximal and distal boundaries of a target in a patient. When we start processing this data, one of the first things we do is remove information that we don't want and carefully keep track of things that we do want. In this example, I've got a PCD spectrum that contains harmonic, broadband, and ultraharmonic components. If we want to compute powers for each regime, it will be important to keep track of the data sorting. So in this case, are we only keeping tone lines, or are we being careful to include shoulder bins to account for the fact that the input signal was finite in length? So a lot of this is just careful bookkeeping and reporting. When we beamform this data, a critical feature is the point spread function, or PSF. And this describes how a finite bandwidth, finite aperture receiver interprets a point emitter at a specific location. In these linear array examples shown here, we see that the PSF is very strongly sensitive to source location. Now, different beamformers will have different PSFs, and adaptive beamformers may change their PSF at a single fixed location just based on small changes in input data. And this is all important to understand when we try to assess energy and dose estimation. You'll hear more about this over the next couple of weeks, including Cameron Smith's talk in week 3. I'd like to continue now with some examples, starting with a single element focused PCD. And one of the things you can see in these half amplitude beam contours is that the sensitive volume is frequency dependent, and the location of the maximum response may not be at the geometric focus. So it stands to reason that the focused PCD can miss some events and alter the apparent frequency response of others, depending on where the emitters were in the beam pattern. If we repeat this measurement with an unfocused device with the same bandwidth and size, we'll get much broader spatial coverage, but less localization capability. And this is where it really helps to have a focused source, so you can limit the locations where cavitation is likely to occur. Now, to compare these two scenarios for measurement, I have driven the emitters shown in the middle diagram with harmonics of 0.5 megahertz. And when they all combine into their respective PCDs, we get this spectrum plot here. We compare at low frequencies, we see that there's not much difference between the two. And that stands to reason for, at these low Ka values, there's not enough phase introduced by the device curvature to make the beam pattern substantially different. But as we go higher in frequency, we can see that the results diverge, order of magnitude or more differences. And the details of all this depend very much on where the emitters were and what they're emitting. Further discrepancies would occur if the devices were not the same size. Now, you're going to see reports later on in this session from clinical systems that use PCDs in both the left side and sort of the right side of the simulation range. Fortunately, there are methods available to us to help overcome some of the challenges with PCD measurements. A really good example of this is from Kyle Rich and the group at University of Cincinnati. Here, a substitution calibration was used to get the electroacoustic response, and a model was used to estimate diffraction terms. These were combined to give a volume-integrated diffraction correction, and when that was applied, it gave a final calibrated PCD result. In related work, Colin and Kousios also used a substitution calibration, but they only did this at a point, and this was because they were interested in monitoring emissions from a single bubble in an attenuating medium. So they combined attenuation measurements with their substitution cal, and they were able to do this and get a very good agreement in comparison with a bubble model in a lossy medium. We're moving on now to examples of 2D imaging where broadband emissions from a single source in an attenuating medium are recorded by two different diagnostic arrays. Images were formed using an adaptive beamformer with a 1% input sound speed error. The displayed quantity is estimated energy normalized by the actual emitted energy, and the peak values of locations are shown in the bottom left of each frame. We can see that the two devices give energy estimates differing by about a factor of 4, and the peak locations are different as well. Now, if we go ahead and move the sources twice as far away, we see elongation of the beams as expected, along with some more shifting of the curvilinear case. If we look at either of these columns of images, we can see good examples of depth biasing that could occur even within a patient if we don't account for attenuation and diffraction effects. And look, there's a lot going on in this slide, I admit, but the main thing to come away with is these are all images of exactly the same source. Methods for mitigating these effects were investigated by Gray and Kousios. Array element sensitivity and diffraction terms were measured by substitution calibration, and attenuation in a lossy propagation medium was estimated directly from the cavitation data itself. The combined corrections led to an accurate recovery of cavitation energy directly measured in water. Some interesting related work has been done by the photoacoustics community, and this is one example. And typically, they want much more bandwidth in their calibrations. And so to get that, they used a laser-excited target. This was combined with a diffraction model to give them their total array calibration terms. We continue now with linear arrays, but for the more complex task of imaging transcranial emissions. In this example from Kostas Arvanidis and the group at BWH, we see how different aberration corrections change the amplitude, location, and detailed shape of their cavitation maps. These examples showed an axial shift of about a centimeter depending on how the corrections were applied. In a series of papers by the group at Sunnybrook, 3D receiver array designs were studied in detail. In this example, first authored by Ryan Jones, we see how a sparse array image of a point source appears first without a skull on the left, then with a skull, and then with different phase corrections applied. And one of the interesting suggestions that's come out of this work is that aberration correction may not be needed at frequencies below about 300 kilohertz. I've tried to summarize the foregoing issues in this table, and I've provided my take on which terms I think are likely to dominate across all scenarios. Of course, the relative details will vary. In my sense, from reviewing the literature, as well as what I'm aware of that's in progress, is that there are no glaring holes in the available methodologies. Specifically, the pieces needed for a complete PCD calibration all seem to exist. We're just about there with handheld arrays for soft tissue imaging, and arguably, methods for the hardest parts of transcranial imaging are relatively mature at this point. So I don't think it's a question of whether it can be done at all, as I think it can. I think really the questions are, how do we put all the pieces together? And when we do that, how good is good enough in terms of making these corrections? As a final technical note, it's worth keeping in mind that cavitation imaging is the new kid on the block in radiology. And so as we start thinking about treatment guidance and dose metrics, it's worth taking a look at what lessons we can learn from more established radiological methods. And a good place to start seems to be diagnostic ultrasound safety indicators. Here we require device calibrations, there's some accounting for attenuation, and critically, thermal index calculations are varying by scenario. And I think we'll want to adopt an approach like this, given the broad span of therapeutic applications of ultrasound that we're interested in. A better corollary for what we're really doing with cavitation probably comes from PET, positron emission tomography. Here, we don't really know where the emitters are going to be, and we need another imaging modality to provide anatomic referencing. But with PET, the detectors are all calibrated, and photon attenuation through the tissue is estimated and corrected as part of image formation. So hopefully we'll take a look at these and other existing radiological methods as we define what we're doing going forward. So to conclude, if you take away just one thing from this presentation, hopefully it's that calibration for cavitation monitoring is not just about hardware. And my apologies to the session organizers for saying that. Hopefully we're agreeing on the considerable benefits to thorough calibration of our signals. And really, the main questions I have are about standardization and adoption. When defining our methods, how good is good enough? And how do we standardize and encourage the usage of these methods? Finally, I'd like to acknowledge colleagues at the University of Oxford and across the cavitation imaging community, who together have advanced the field to a remarkable degree in a seemingly short time frame. Thanks, everyone.
Hi, Michael. Thank you. Thank you for the excellent presentation on related to considerations on how to calibrate cavitation signals that we are recording. And I guess the order of your presentation clearly indicates that the organizers are acutely aware of the complexity of the task and the different dimensions that we need to take into account while we're trying to come up with a way to quantify the emissions that we're recording. But let me start from a first question that I was thinking about. You said like there are all the key components are already there, and there is already a lot of work going on in that field. So what do you think are the key components right now that potentially every lab should kind of like consider using? And I will just say a few things with respect to: do we need calibrated sources? Do we need calibrated receivers? Do we need specific algorithms? What are the things? How would you order the importance of the different components that we need to have?
I was worried you were going to give me a hard question.
I keep them for the end.
Well, I guess first of all, to be completely fair to the practitioners, I mean, there are some instances where some of these calibrations will not be necessary, right? I mean, if you're using an internal standard and looking at elevations relative to, say, a pre-therapeutic emission level, that may work perfectly well. And then the only thing you'd have to worry about is if you change out a piece of hardware, is your standard still usable? So I think it becomes more of a question of when you have to try to compare data across groups, across systems, and across patients, even with your own system, the patients change every time. There are a lot of internal biasing factors that you still have to worry about, even if your hardware system never changes. And so I think we can't prescribe we wouldn't even try, but we wouldn't prescribe a one-size-fits-all for everybody. I think it's a discussion to be had about what's good enough for certain kinds of internal references versus wanting to establish community-wide dose metrics that anybody can use. And I think that's something we, as a group, have to develop.
Okay. Thanks for. So, do you think that is there a calibrated source, for example, right now that everybody will be able to use for those reasons? What are your thoughts?
Well, yeah, I think for the electroacoustic part, for the diffraction part, it's certainly possible to get a good broadband source made just from a scattering experiment, and those methods are pretty well established in literature right now, and they're not terribly expensive to implement either. Mm-hmm. So that's the good news. I think it's more about time consumption, that if you want to explicitly measure a lot of these functions over a suitably wide range of treatment scenarios, say multiple depths from, 20 millimeters out to 100, it's just physically a lot of time to expend, and you need the resources to be able to kind of get all that done. For attenuation, it can be as simple as using book values, and then that's another discussion to have as the community, is whether you want to trust them or not. Yeah. You can certainly take sort of organ averages, things like this. But if you look at how wide the spread is, there's a good argument to be made for doing in vivo estimates instead. Mm-hmm. It's just that that's not going to be appropriate for every practitioner either. Sure. And then similarly, well, both for attenuation and sound speed, the world is full of ultrasound-based estimators and actually CT or MI-based estimators for these quantities. I personally always advocate for trying to get the in vivo data if you can. And we'll just have to analyze, I think, what's the risk in dosage estimation between taking historical averages versus what may reasonably occur in a specific patient or treatment scenario.
Oh, that's an excellent point. I would like to pause here so we can move to the next talk. But I would like to ask you to please stay with us until the end, because I would like us to continue this conversation at the end of during the panel discussion. That's an excellent point. Thanks a lot, Michael, once again for your excellent presentation. And I'd like to move to the next talk, which is going to be from Nathan McDonald, and it's going to be on transcranial hardware.
All right, thank you for this opportunity. My name is Nathan McDonald. I'm at Brigham and Women's Hospital in Boston, and I'm going to talk today about transcranial cavitation monitoring hardware. Before I start, just to disclose that some of the work I'm presenting was funded with a sponsored research agreement with Insight Tech. So I'm going to talk about two different applications for transcranial cavitation monitoring that I'm familiar with. The first is transcranial thermal ablation. This is done with the Exablate Neurosystem from Insight Tech, as you can see here. In this helmet, we use to apply thermal ablation in the brain with transcranial sonication, and the cavitation detectors are built into the helmet. And this is a FDA-approved treatment for thermal ablation in the thalamus for tremor, and it uses active control based on acoustic emissions. And what this is for safety. So during each sonication, the detectors built into the helmet monitor for subharmonic emission. And if it's detected, it will automatically lower the power in real time to maintain a safe level. And the goal here is to avoid cavitation for safety. If you have inertial cavitation, there's a risk of hemorrhage, and they don't want this in this thermal ablation treatment. Another application for transcranial monitoring with this same system is for aberration correction. So the system uses acoustic models and CT based on CT scans to correct for the skull. And you can get a better correction with that if you have some sort of measurement to guide the correction. So the idea here is that they will use a low dose of ultrasound contrast agent, and with pulse sonications and an iterative approach, they can use the signals coming back to correct for the skull. And compared to the regular CT-based focusing, they saw an increase in efficiency and the size of the focus. And this was published recently by Ryan Jones from Clarbo Hinnan's group at Sunnybrook. And this is nice. That is, if this is successful, then this can increase the patients that can receive this treatment, which is currently limited by variability in the skull. Most of the work that I'm familiar with looking at transcranial cavitation monitoring has been in the context of blood-brain barrier opening. We've been working on this for a long time. These are some results from Costas's paper when he was at Brigham with Marge Livingstone at Harvard, where we were looking at using the clinical exablate device for BBB opening in monkeys. And this is with our own detector that we put into the system. I'm using a narrowband detector that's sensitive between second and third harmonic. So when we see broadband noise, we see it as this narrow hump. And what we see when you start increasing the power, and this is generally true for BBB opening, the first thing you see is a very large increase in harmonics, so second, third, fourth harmonic. Later at higher powers, you start to see subharmonic emission, ultraharmonic emission, and then very close by, a very small step, you get broadband emission. And the general goal is for us to get stable cavitation without wideband emission or inertial cavitation. So we want to stay in this zone where we see harmonic emissions. And the reason for that is that when you see inertial cavitation, you start to see some petechia or vessel damage. And this was some results from that study where we looked at different targets. And when we saw broadband emission, we saw these effects in histology. And when we didn't, we just saw harmonic emission only, we didn't see that. Sunnybrook has taken a different approach, and they have some very nice results in their preclinical work using subharmonic emission. So instead of looking at the magnitude of the harmonics, they're looking for the onset of subharmonic and ultraharmonic emission. And the approach that they use is they ramp up the power until they see ultraharmonic or subharmonic, and then they back off by a predetermined amount. This is a very nice approach because if this threshold for subharmonic emission is independent of what tissue you're in, it gives you a sort of calibration of the pressure that you're at. And that's assuming that you can detect this threshold above the noise floor. And they've done this in thousands of experiments, and it seems to work really well for them. And they've actually looked at this also in their early clinical work. As I mentioned, we've been looking at sort of in a similar way where we, instead of looking for a big increase in the subharmonic or ultraharmonic, we look for a big increase in the second harmonic. And this is compared to the same sonications applied without microbubbles. So instead of looking for ultraharmonic, which may be very close to the damage threshold, we ramp the power up until we get to a predetermined level of harmonic emission. And then we actively control the power to get it within this band, which is our controller goal. And then if we're using a bolus injection, we stop the controller and just use a fixed power after that. And if we see any wideband emission or subharmonic, which you can see down here, it can be a very small signal, we'll drop the power similar to what Sunnybrook does and back off and use a fixed power after that. This has been published by a couple of studies by our group. This was from a few years ago, looking with the exablate device and the nice thing that we've been investigating with harmonic emissions is we can relate this to the amount of drug or tracer that we get into the brain. Here's a study, this was from Tao Sun in our group, where we looked at using another low frequency system, a lab system in this case, where we looked at the delivery of trypan blue, which is a tracer, and doxorubicin. And we could see that both in the tumor and in normal brain, we can see a relationship between the amount of drug that we got in as compared to the harmonic emissions. We've been recently trying to use this in a more clinically relevant scenario. So again, with the exablate helmet, we have our own cavitation detector, and we're starting in rats again, where we put a human skull sample between the transducer and the rat. We're also going through the rat skull, so this is actually doubly transcranial. And we see the same thing as what we saw without the human skull. So as we go up in power with the exablate device, the first thing we see is a very large increase in the harmonic emission. And again, this is relative to acquisitions made without microbubbles. So we're taking into account any sort of baseline harmonic emissions. And then later we'll see an increase in ultraharmonic, subharmonic, and wideband emissions. So we see this very large signals. Again, our goal is to be within this range here, where we know that the magnitude here is going to be related to the amount of drug that we get in, and that we should be able to do this without damage. Looking at some more results from this, this is an early study where we compare different emissions when we have a human skull and no skull. These are in 2 rats. With a human skull, I targeted 80 different targets in 1 rat with the Exablate device and measured the thresholds for harmonics, 6 dB in harmonics, which is a reasonable jump to look for, ultraharmonic, subharmonic, and wideband emission. And we can see that there's a lot of variability, even though we're in the rat, which is this tiny little brain, and steering around. We see a huge difference in thresholds, but overall we see the same trend. And with harmonic emission, we don't see for above the threshold, which we might use for a controller, we're generally not going to be above the wideband emission. And when we start to look for thresholds for subharmonic and ultraharmonic emission, at least with our system, we see often the threshold is actually higher than what we're measuring for wideband emission. And then comparing these thresholds with the skull and without the skull. Again, these are early studies with 1 skull and just a couple experiments, but we can get an idea of what the attenuation is. So it's around 60% if you compare the threshold. This is the insertion loss in pressure amplitude. So you can see that there is still significant loss, even though we're at a very low frequency with the 230 kilohertz of the low frequency Exablate system. We're going to hear more about this in this session from Insightech, but we've also been having some experience doing cavitation monitoring in patients. So we're a part of the trial, multi-center trial, where we're trying to deliver chemotherapy to patients after with brain tumors after surgery. So here we're not delivering drug to a tumor, we're actually delivering drug to brain tissue with a goal of getting chemotherapy to infiltrating cells that are protected by a blood-brain barrier. And you can see this is one of the planes we targeted. We do hundreds of targets. This patient we treated 6 times over 6 months. And you can see that we get, in the contrast enhanced imaging, nice disruption. You can see it's going along the fibers of the in white matter. But unfortunately, and sometimes we'll see petechia, and this is in susceptibility weighted imaging, which may be overstating what we're seeing here. But we definitely are seeing some evidence of petechia after these procedures, and we would like to avoid it if we can. So I've gone through, and for each of these treatments, I calculated in a small ellipse centered on each of the targets, the percentage of the volume where we had BBB opening and where we had petechia, and plotted them as a function of the cavitation dose. And with the Insightech system, they're using subharmonic emission to control the power actively during these procedures. Now you can see that we did about 2,500 targets over these 6 treatments in this one patient. Each of these dots is a measurement from one subsonication spot. And there's a huge amount of variability, and that's not surprising. This is a somewhat problematic fuzzy measurement. We have registration errors, and there's overlap effects where one sonication may affect something in its neighbor. But on average, we can get an idea of what the relationship is between the cavitation dose and the BBB opening and vascular damage. And you can see on average, so here I've binned all the data in these areas by these vertical lines. You can see there's a clear relationship between amount of BBB opening and petechia that we get as a function of the Insightech's cavitation dose. And you can even see that there's a small window here where we can get BBB opening with low probability of having susceptibility weighted imaging. Of course, we would like this all to be 0, and that's hopefully what we'll be able to achieve going forward. However, what we've seen is a large variability from case to case. So here, looking at 5 more patients, you can see, doing the same analysis, that there is some trend where there is some agreement in some patients. But for example, in this patient, we applied a much higher cavitation dose, a much higher power level, but we got much less opening and a very low amount of petechia. So there's a lot of, we still have some work to do on this. And I think the reason that this is different than what we've seen preclinically is that we're using lower microbubble doses in our patients to allow us to start sonicate large volumes. We need time, so we're using lower microbubble doses than what we use in preclinical work, and we're infusing them. The targets that we're looking at least in brain tumors, are in white matter, and the low vascular density is much lower there. So the signals that we use for acoustic emissions are going to be much smaller, and we see a very large variability between patients. We didn't have that in our preclinical studies. So we need to be able to take all of these into account. So going forward, I think that the future directions for transcranial cavitation monitoring, we need to do a few things to get better results. I think first we need to calibrate our detectors and publish those calibrations. I think we need to be able to compare what we're doing from different sites and get a better idea of what we're actually measuring. For transcranial use, I think we need to have treatment planning not only for correcting for the skull for transmission, but for taking that into account in our cavitation monitoring. And that's going to involve including skull attenuation and aberration, maybe beam steering, and vascular density to improve our monitoring and our control. I think that with the low levels of bubbles, and especially in white matter targets, we need to really increase the sensitivity of our detectors. I suspect that we're getting wideband emission below our detection threshold, but that's to be seen. And then ultimately, I think if this is successful, we're going to move from cavitation monitoring to cavitation imaging. And I think that that approach has really been demonstrated by the group in Sunnybrook with their lab-built device, where they built their own helmet that have both transmission and receive capabilities. So they have many more detectors, so their sensitivity is going to be much higher than with single detectors. They can take into account beam steering easily, and they can get, I think, better quality, and not only know where what the strength of the emission is, but where it's coming from. So I think if going forward, in my opinion, this is ultimately the way that things are going to go. And this solves, I think, some of these problems that we're seeing in these clinical trials, which overall have been very, very encouraging. But I think we still have some improvements that we can make. So this is a study published by Ryan Jones. There's a number of other studies on this hardware that they've built. And you could also use this technique or technology to look at microbubble concentrations. And I'll end by pointing to this paper by Megan O'Reilly. It was a very beautiful study where you can look at microbubble concentrations at very high resolution using this passive acoustic mapping transcranial array. And with that, I think I am done. So thank you very much.
Thank you very much, Nathan, for a very inspiring lecture. I wanted to ask you specifically in the context of the skull, what do you think we need to do to get rid of these AU units that appear in your cavitation measurements? You refer to the importance of calibration in your final two slides. What do you think are some of the challenges in getting rid of arbitrary units for specifically BBB or brain treatments?
I think that we've generally been looking at, driving the exposures until we see a threshold event, whether that's, ultraharmonic emission or an increase in harmonic emission compared to what's before, or wideband emission for safety. And I think the first thing we need to do with these calibrations is at least to get an idea of what the sensitivity is of our detectors. Because if you're using that sort of approach, everything is about how sensitive you are, and are you missing activity. To do cavitation dose is going to be a lot more complicated, especially with a transcranial approach, because then you need to bring in models of the effects of the skull, not only on the transmit, but on the receive side. And, I think it's possible, but it's going to be challenging. And there's always going to be this sort of, we're injecting microbubbles and we have a very wide range of vascular densities. We also need to know that information. I mean, in the end, we need to know if we have a small signal, is it because we're not at the right exposure level, or are we just don't have any microbubbles there that we're listening to?
There's a question here not directly relating to cavitation detection, but I think it is a very good question that I want you to have the chance to answer. So do you think using higher bubble dosing may be useful to better correlate preclinical results to clinical results?
higher bubble doses in humans.
I read the question to mean, would we get better comparability and better predictive ability of the animal studies in humans if we use the same high bubble concentration?
I think that would actually help a lot. And at least in the US, the FDA has begun to relax the doses that we can use. So hopefully going forward, that'll be less of an issue. You do need to take care that if you are operating above the inertial cavitation threshold and you increase the microbubble dose, you're going to get a lot more damage. So there does seem to be some caution involved there. But yes, I mean, or we need to go back and, do these animal studies and try to improve what we're doing with lower microbubble doses and infusions of microbubbles instead of bolus injections.
And two final questions, very briefly. Your thoughts on what units would be most appropriate for a calibrated cavitation dose relevant to BB opening?
Well, again, I think, if we have the ability to detect a threshold event that has a physical meaning, I think I like that approach. And there we need to just understand that what the sensitivity is. And I think that, one could simply use calibrated sources to try to characterize in space and frequency your detectors. Ultimately having a meaningful cavitation dose would be fantastic, but like I said, it is complicated.
And finally, can you expand on the variability among patients seen in the cavitation dose? Seems problematic with respect to BB opening prediction.
Well, there's a lot of, we have a lot to learn. I mean, some of it I think a lot of it is just where the patient was. I mean, where the tumor was in the patient, it varies all over the head. So even though we're at a very low frequency, the geometry of, the transmission angles vary, distances between the detectors and the focus vary. So on a first order, I think, we're good looking at safety, the way that it was intended to use, but I think we need to start adding more information that we get from treatment planning to these cavitation monitoring.
Thank you very much, Nathan. Thank you for a brilliant lecture. In the interest of time, we will move to the next speaker, but please stick around for the panel discussion. It gives me great pleasure to introduce Elisa Conofago from Colombia on clinical implementation of single element PCD.
Okay, hi everyone. My name is Elisa Conofago, and I'll be talking today about our experiences with clinical implementation of single element passive cavitation detection. So this is going to be in the context of blood-brain barrier opening, which uses microbubbles and focused ultrasound, or FUS for short, as we know, to target the specific regions of the brain where we want to treat to deliver either drugs or induce an immune response. This is what we have as a clinical setup concept. I'm going to talk about a little bit about the neuronavigation. We use an infrared camera that uses fiducial markers on the face and also on the transducer itself to target the region that we see here on the right. And then we plan out using simulations, finite element simulations, and to be able to predict where the focus is going to land. And then, of course, what we're here for today, which is basically monitoring the cavitation event. We published this a few years ago now about the mapping. I'm going to end with that. I'm going to focus mainly on the detection, but also the mapping. And then finally, using MRI to assess where the opening occurred and how far was it from the planned region. This is what our system looks like. We published this last year. We also presented a lot on that this year and last year as well, also as part of the FAST workshop on blood-brain barrier. So this is, again, the infrared camera here that I mentioned, the transducer, which is at 0.25 megahertz, that is used to open the barrier. We have trackers on top of the transducers. I'm going to show you a magnification of this in a second, and then a robotic arm that makes sure that we have millimeter precision to position on the patient's head that sits in this chair, completely awake, and the whole procedure for opening is about 2 minutes. Now, the advantage of this is the fact that you can use the pre-acquired MRI and then identify where you want to target, similar to what I showed you in the previous slide. And the crosshairs allow you to see how well you're centering in red here, the bullseye, to the actual intended location. This is what the planning workflow looks like. So with a position, we position on the patient's head. This is an Alzheimer's patient, our first Alzheimer's patient, in fact, and the transducer is in green here. And the hole that's in the middle, that's actually what houses the PCD. And on the right is the actual numerical simulations on K-wave in this case, where they can predict where the actual focal spot will land. And this is at minus 3 dB pressure here. We also have done over the years the prediction of the aberrations through the skull for the actual focal shift in both the axial and the lateral direction, which is on the order of a couple of millimeters. And then we also have more recently shown that we can get similar accuracy and under specific conditions to what we see in experiments, depending on what simulation package we use. Now back to what we're here for, which is basically the treatment monitoring. These are actual in vivo data, clinical in vivo data that I'm going to show you also later on. As I'm going to mention, we actually are in real time monitoring harmonic cavitation, ultraharmonic, and inertial cavitation. We also forming spectrograms that allow us to see the frequency content, and based on the frequency content, also the occurrence of cavitation. And the special occurrence of cavitation. The mapping is what I referred to earlier. I'm going to end with that, as I mentioned. And also just a heads up that we also have alternatives to gadolinium. We published also earlier this year, where you can use diffusion-weighted imaging to identify in a contrast-free MRI where the actual opening happened, which I'm not going to cover today, but this is just to show you the entire pipeline. So these are the two clinical trials that we have currently ongoing in Colombia. The first one, as I mentioned, is an Alzheimer's clinical trial that started last November, where we're opening the blood-brain barrier in Alzheimer's patients, using focused ultrasound and microbubbles without a drug. And then the second one is a pediatric tumor clinical trial that started just this past month in August. And we're using focused ultrasound to open the barrier together with oral delivery of panobinostat in children with progressive diffuse midline gliomas. So I'm going to first give you the update on what we do with the Alzheimer's clinical trial. This is the same setup as I showed you before that we're using on the patients, which basically has the PCD in the middle of the transducer. These are the exclusion and inclusion criteria that we have for the 6 subjects that will have a mild cognitive impairment or early stage Alzheimer's as some of the criteria. And we are targeting the prefrontal cortex with subsequent MRI and PET. This is the magnified version of what I showed you as a setup earlier, which has the PCD, the reflective beads that are monitored continuously by the optical camera, the robotic arm that we use to precisely position the transducer on, in this case, on the right side of the forehead of the patient. You can make out the actual void in the middle where the PCD is inserted. And of course, we position with a neuronavigator, and we constantly, during the procedure, are acquiring the cavitation signals, so that come through the stable cavitation, either unstable cavitation, which is basically inertial, but also both broadband, which is obviously relates to unstable cavitation, but also to harmonic and ultraharmonic. First, we acquire the time domain signal. And then, of course, we do a FFT of that, and we're able to identify above a certain frequency the harmonic, as I mentioned, cavitation dose that relates to the beams here. That are the harmonic of the frequency that we're using at 0.25 megahertz. The ultra harmonics, that are the ultra harmonics in between, half harmonics between the harmonics of the actual focused ultrasound, and of course the broadband response throughout the entire frequency. Now notice that our PCD has a center frequency of 1.5 megahertz, and therefore we have a bandwidth within around this 1.5 megahertz, which we trust to be accurate, and we perform cavitation, those calculations that we then display in real time during the procedure. Now, I'm going to show you in real time what we see while we're opening the barrier. So these are the signals that are displayed in real time. Of course, we have accelerated a little bit to cover the 2 minutes that the procedure is on. So we, as I said, we can do the 3 different doses: harmonic, ultra-harmonic, and inertial. And of course, we can also display the spectrogram that allows us to see both the frequency content, but also according to the magnitude of this of the actual FFT or the spectral amplitude, where exactly the cavitation will have occurred. So obviously, the higher the attenuation, we believe in the brain that has crossed the skull. So these are the attenuation, and then closer to the skin or the scalp, we see these particular signatures, but also notice that they're centered around the center frequency of the PCD. The other very interesting aspect is the fact that through the cavitation, we can actually make sure that the bubbles have reached the focus, and it takes from injection IV about 15 to 20 seconds to reach that, depending on the target. In this case, the prefrontal cortex took that, and we have a sustained inertial, but much lower than what we have harmonic and ultra-harmonic. Notice that this is a logarithmic scale. And compared to what we know a lot through transcranial cavitation detection that we base on the clinical for in the NHP, we see that the harmonic to broadband ratio that we have at the frequency of 200 kilopascals for the NHP and 400 kilopascals for the NHP is very similar to what we find also in humans. In fact, it's about 10 times harmonic and ultra-harmonic amplitude compared to the broadband. And this is some of what we see on the screen. This is literally during our first opening of the Alzheimer's patient that I already showed you, the one on the top right. This is how we're targeting the patient sits on the chair. And we have constant cavitation monitoring after targeting with our neuronavigator. And this is the result, the blood-brain barrier opening. It has opened in the region that we intended, and the actual volume was around 4 centimeters cubed. Now, for the second clinical trial, I'm not going to show all the steps as I showed in Alzheimer's, but it's very similar to what we do for those patients. The difference is mainly that we're going through the back of the head. This progressive diffuse midline glioma occurs in the pons, the pontine gliomas, and therefore it's basically between the spinal cord and the tip of the brain. So we're targeting in the back. A couple of issues that could be there is that we're going against gravity. So some of the coupling is a little bit challenging. And also the back of the head has a thicker skull than the prefrontal cortex region that we targeted earlier in the Alzheimer's. However, again, through the actual simulations, we're able to target and compensate for the attenuation that we're expecting, and this is some of what we're expecting, which is basically in the palms of the actual patient, and this is what it looks like with a pediatric patient that we have, as you can see, the same transducer. Again, the PCDs in the hole here, and we're able to target the back of the head with the same way that we did before with the neuronavigator. And the same way that we did before, we also are able to see when the bubbles reach the target. Now, in this particular case, it took a little bit longer after 20 seconds. And there was a sustained inertial cavitation together with harmonic and ultra-harmonic. And for this particular patient, you can see the blood-brain barrier opening, the gray matter very targeted in this region in all 3 slices. And we can also see for the second patient that we had a couple of differences. One, much lower inertial cavitation than harmonic and ultraharmonic. So it allowed us to actually see that in this case, we sustained more harmonic cavitation, stable cavitation than unstable. And the second thing is that it was not as clear from the harmonic and ultraharmonic that the bubbles were entering the focus. However, that was a little bit clearer on the inertial. The same thing with the spectrogram, more of the attenuation that was happening, and then we can actually see that and detect it by similar center frequency around 1.5 megahertz. And the opening that we saw was also more diffuse and a larger region, again on the pons compared to the first subject. What I want to end with in the remaining minute that I have is that we also have been able to do this in patients with passive acoustic mapping, which is basically imaging with an array now instead of a single element transducer in the same region. And we use the Verisonic system to acquire that. We use the coherence factor passive acoustic mapping, and we calculate the coherence factor that would then display also in real time. And this is some of the what we can do in both the PCD at the same time as the passive acoustic mapping that allows us to spatially, in this case, identify where we actually, in the general sense, where we actually have the highest cavitation. And here's what you see in the spectrum with both the inertial, the stable, and ultraharmonics, the ultraharmonic signal. So we have tried a few algorithms that I don't have time to talk about here in the brainstem, and we are able to see that they have a similar maps. Our favorite is, again, the coherence factor that has a computational time very similar to TPAM, but and also very similar resolution to ES-RCB. I want to end with this slide where we have the great team that I have highlighted here in bold. And of course, our great team at the Ultrasound and Elasticity Imaging Lab, all our collaborators in neurology, oncology, and also what makes it capable to actually do clinical trials at Columbia, which is the Clinical Translational and Science Award. And of course, the Focused Ultrasound Foundation and the NIH funding for this, and of course, a great group. Thank you.
Also, you're on mute.
Yeah. So, hi, Lisa. Yes, once again, thank you for sharing with us your excellent progress with the clinical system and your fascinating results from the clinical trials that you have already initiated. Let me start with a question. I found quite interesting the metric that you used, and this was the ratio of harmonic to wideband emissions. And that kind of like also reflects several of the things that we have discussed today about calibration, whether absolute or relative measurements are important. Can you please comment on that and how this metric really kind of like captures the effects that you are interested in capturing right now?
Yeah, sure, Kostan. Thanks for having me today. So the main thing is obviously because we were getting broadband and this is something that, like Nathan very well described, we have linked it to potential damage across all the species. Although I can say something at the end about that, how reversible versus irreversible sometimes. So long-term versus short-term damage, how it plays out. But in any case, we found exactly what you say, that we can't really have an absolute value. So there's a lot in PCD that you do blind still. I mean, it's much better than no PCD, absolutely. So we love PCD, and the monitoring is very important. But there's still a lot that you don't know. You don't know what incidence you're hitting the actual skull with, whether you're getting a normal incidence or whether you're deviating. How much of that could be actually side lobe, main lobe. And also, the fact that the skull is very uneven. It's not just the thickness, it's also highly inhomogeneous. And we found that it's very difficult to go with the absolute cavitation dose from one subject to the other, or even from one location to the other. So the main thing would be, once you start comparing across species or across even animals or subjects, you have to have a different metric, and we can discuss this later, I'm sure. And we thought one of them will be the harmonic versus broadband ratio, and how it varies between subjects and also between species.
Yeah, that's an excellent point. And there is a question here that about the experimental methods and mostly the components. What was the nature of the microbubbles in terms of concentration, size, and material? Do you use clinical grade? I guess you use clinical grade bubble, right?
Yes, we do. As some people know from our publications in the past, and that was the question also that Nathan very nicely answered, that whether the dose makes a difference. So we obviously had to comply with the FDA, and the recommendation was the imaging dose. So we are using 1x of the clinical dose for imaging. We have found that obviously in animals, both in mice and in monkeys in our case, it does actually, increasing the dose doesn't always mean that you're going to be on an unsafe range. I mean, once you do your proper calibration, you know that you can sustain stable and in fact, even get this ratio that we just talked about even higher, because you do have the mass that you need to open and to sustain it with a stable cavitation. So we really think that that relaxing those measures are key to therapeutics. But we are using the clinical dose through both clinical trials.
Okay, and I guess, there's one question just to confirm that you acquire all PCD data throughout the treatment and you have all the data available.
We have all the data available. Without PCD, I have to say we cannot, the MRI sometimes is very inconclusive because, we're getting these tiny openings, and especially in some of the pediatric subjects, because we're talking about diffuse gliomas, a lot of inflammation, a lot of enhancement on flare, and even sometimes with contrast enhanced MR. So we trust the PCD sometimes that we have opening, and we can. I'm sure it's going to come up with in this workshop more sometimes than the MR itself.
Excellent. Thank you, Elisa, once again. And please make sure you stay around for the panel discussion where we will potentially revisit all these topics so that they are not we cannot address them in so short period. And with that, I would like to move to our final presentations from Itai Rachmilevich. Is on implementation and use of PCD using the Exablade system. I'd like to say, due to time differences, Itai will not be able to answer any questions, so we will break after that. Okay.
Hello, everybody, and thank you for joining our session. Today, we will talk about exablade cavitation and detection, its management and usage for the focused ultrasound treatment. We will have some introduction, a general overview. After that, we will talk about the ablative system, the cavitation detection and control that is being used, the role of the cavitation for managing the BVP opening treatment, and at last we will talk shortly about the echo imaging treatments that were recently launched. The role of the cavitation saw a significant change and growth within the recent 10 years, so to say. Cavitation is, of course, a threshold phenomena. Positive feedback may be violent, can be used, but should be also taken care of. In our first brain treatments, we actually did not use cavitation detectors. It was not before a very early stage when Professor Daniel Germonot of Zurich published his case report of an adverse event that we realized that cavitation detectors should be introduced to the system. We then introduced first 2 cavitation detectors, and over the years we have added cavitation detectors. Now it stands on 8. And in some systems, we use even higher number. You will see it in the coming slides. The detector's response is used actually to control the cavitation in order to keep the sonication safe. In the future, we aim to add multi-elements-based cavitation detection and manipulation to enable detection and localization of the source of the cavitation. This is actually the paper by Daniel Jamonot that was reporting of the complication with ischemia and bleeding. Cavitation is being used also in BBB treatments. The difference is, of course, that cavitation in the ablation treatments is induced by pressure, not by administrative bubbles, whereas by BBB treatments, we are actually injecting the microbubbles in order to activate them at a very localized location to facilitate the BBB opening. The real-time analysis of the system of the microbubble spectral response is being used for closed-loop control. We call it a controller of the opening and the required spectral dose. This slide shows actually the general graph of the cavitation phenomena, very simplified, of course. You can see here the inertial cavitation that is describing oscillating bubble that is ending at implosion, and a stable cavitation that keeps oscillating. Really, Plesset model can describe to some extent the stable cavitation. You can see here also the two graphs that are being shown to the user. Below you can see the graph of the amplitude that is being recorded from the target versus the frequency. You can see the driving frequency, of course, 680 to 650 kilohertz. And we are looking basically at subharmonic of half frequency, where the cavitation has some signature, in this case, a very tight spike. In the case of the inertial cavitation, the explosion or the inertial cavitation phenomena releases a wide band of frequencies that we can read. We analyze both, and we take the information of both into account in order to manage and manipulate the safety of the treatment. What we can see here is actually our transducer. You can see here, of course, the matching layer with the tiles and the 8 detectors that are being placed on the transducer. Those detectors are actually configured in a fashion that is tuned to listen to half of the frequency, which proves so far to be effective over some thousands of treatments. The wide activity function of the detectors is being set so in order to recognize cavitations that do not originate only from the target itself, but from different regions that can be a little bit further from the target and maybe of importance. We do have the triangulation option too, basically embedded already in the system. We use the chirp localization system, of course. It is at the moment not enabled, but we consider to use it in the future, this or another way of localization. What you can see here are 2 elements. On the left hand, you can see the transducer element itself, and on the right hand, you can see a cavitation detection element. Here we look at, we start to talk about the closed loop control, which plays a very important role in our treatments. Basically, we would like to control the cavitation. In the beginning, we had only a stop sonication mode, which meant that once there was a cavitation that was reaching a threshold of safety, we have several thresholds of safety that we have basically found by the pre-clinical experiments that we have done prior to the first submissions that led to the treatments. So if the cavitation level would go to these levels, the sonication would stop. And in that case, many treatments would stop. Then we have introduced a closed loop control, which means that once the cavitation is climbing in the direction of the limit, our system will recognize it, will put down the power, the cavitation will go down. the power will go on upwards and so on. And this is a very schematic diagram of the system, of course, the conducer and the blades, etc. What we see here is actually another description of what we have just discussed until now, which is basically, you can see here the spectrogram, frequency versus time, of course. You can see here the driving frequency at about 650 kilohertz and the response of the bubbles at subharmonic. We are all, until now, we talk only about induced cavitation by pressure. We have not administered any bubbles. This is ablative treatment. You can see some phenomena here that may mention or look like a bifurcation, if you know the paper by Paul Prentice on that. And we are looking here at the subharmonic area. And basically we look at several bands, not three, but I've put three here. We look at several bands at different widths where we are making some calculation, some integration and some calculation over the bands at each time point. So at each time point, there would be a calculation over this band, over this band, over this band. The result, the score for each time stamp would appear as a score that we call the cavitation score, the dose. And you can see here the scores for each of the bands, colors match. What you can see here that from the beginning of the sonication, this is ramping up and then the sonication started, you can see that there was no cavitation and at a certain moment the cavitation was going up. And the score was telling that. Once the cavitation was going up, we have decreased automatically the power in order to cause the cavitation to relax, which indeed happened. Once it was relaxed, the power was automatically going up and the cavitation was not there for a short while, then jumped again and go down. We may note that coming back to the same power would not bring the cavitation to the same level as a general rule, or bring back the cavitation at all. Of course, this is a nonlinear phenomena, so there is no linear relation between the two. After having spoken about the cavitation control, it's maybe nice and of interest to talk about the amount of cavitation that we do see. We see, if we look at a cohort of about 2,000 treatments that I have taken from the recent years, we see about 5% of the treatments do see cavitation stop, sonication. And we see about 58% of the sonications were modulated from the ones that were not stopped. We need to note that the modulation doesn't mean that the modulation comes from the actual target. Actually, the cavitation can originate from a different location. It can originate from perhaps CSF or even the membrane very much outside on the setup of the connection with a patient or from the skull. We do believe that the amount of cavitation from the actual target is lower than this number, and coming triangulation and localization will tell us in the future. Until now, we have talked about ablative system. Now we will go for the BBB system and treatments. In the BBB treatments, basically what we have is we administrate bubbles, we activate them with the phased array. The phased array is important here because we activate really tiny points, which are the subspots that are placed within the region of interest. So we would like to tailor made really a very tiny region or large region, but very specific drone. The phased array can do that, of course. And not only that, we would like basically to be able to give to each one of the points his or her spectral dose that they deserve and being asked. So the phased array can do that too. What you can see here on the video is actually the real-time response like we saw before. We see the same real-time response in the ablative treatment. We can see here the x-axis is the time. You can see here the calculated dose per time stamp and the power that is being changed by the controller in order to facilitate to achieve the dose that was set. So for example, for this treatment, a certain dose can be set, like 1.5, and then some points reached it and other not. Then sonication can be repeated to reach the dose in all the points that we have targeted. Once treatment has ended, we are looking at the post-treatment images, MRI images in this case, in order to evaluate the result of the treatment. What we see here is the result of one treatment published by Dr. Park So-hee and Professor Jin-Woo Chang of the YMC team. We can see here quite localized, very precise pattern of the dots that we have targeted on. Of course, this is again possible due to the large F number, the many elements that can facilitate constructive interference, of course, in each point. In addition, the number of detectors that we use can also assist the control that is so needed to achieve to this result. The last thing that we will talk about today is the echo imaging system, previously autofocusing colds. Basically, what we do here is we wanted to solve the problem that we cannot place a hydrophone into the patient's head. Because when we use, in experiments, we place a hydrophone, we use ACT maps, acoustic correction table, map that we read, we put them back, and then we know what is the best phase correction. Otherwise, we use the CT, where we have written the models, our team, myself included too, that can calculate the phase correction based on the CT and see for more or less best phase correction. In this case, we tried to give an optimal or perfect phase correction. We tried to basically create kind of a hydrophone in the brain of the patient in a safe manner. The administrated bubbles, similar to the BBB, are being administrated, and after that we are sonicating with low power, some tens of watts, to the target, activating the bubbles. The bubbles, when they hear the sound, when they're under the oscillating sound, they start to dance, similar to us, and then they send back their voice. We read that, we analyze the phase of each one of the elements, and of course, we can get the phase correction, the optimal phase correction. We reverse it, of course, and use it for optimal focus. After that, we keep this ACT, acoustic correction table, and use it for the ablative treatment that comes after that, which will use not the tens of watts that we have used for this echo imaging, but use just the normal acoustic wattage that is needed for the treatment. What you can see here is the map, the umbrella of the phase correction that was read, as well as the relative amplitudes that were passing the skull. This is of interest and high importance for further research and analysis of optimal passage and energy delivery through the skull. So to summarize, cavitation monitoring is a key safety element in any focused ultrasound therapy. It is not possible, I think, to perform focused ultrasound therapy without cavitation monitoring and also control. The number of detectors, the multiple detectors and transducer geometry is supporting actually the cavitation signal localization, both the formation and the localization. The tissue local inhomogeneity leads to the cavitation signal to appear under widely different acoustic parameters. For this reason, we need to monitor that in real time. So far, we have about 5,000 or more fast treatments for a variety of treatments, as you know, with cavitation safety thresholds proved to be robust and effective so far. We do follow it all the time and analyze on a daily basis the treatments to see if anything should be changed, but so far it looks very interesting and good. Therapy is based on cavitation, for example, the BBB opening, require real-time control mechanics for controlling efficacy and safety with proper spatial localization. In the future, we will continue to improve the spatial and temporal resolution. as well as we will look on additional ways to quantify cavitation spectra with tissue response. Thank you very much for your joining. It was a pleasure to talk with you, and we'll continue in the questions and answers session.
Thank you very much to the speakers for these very exciting presentations. We will take a 10-minute break, and we will resume with a panel discussion with the speakers who will be joined by Ron Roy from the University of Oxford and Tom Matula from the University of Washington. The Q&A remains active for you to participate. See you in 10 minutes.
Welcome everybody on the panel discussion on cavitation detection equipment. So in this panel discussion, in addition to the presenters that we had during the morning session, the panelists will include Professor Ron Roy and Tom Matoulas, which I would like to briefly introduce now, so as they didn't have the chance to give a presentation this morning. So it is my great pleasure to introduce our panelist, Professor Ron Roy. Professor Ron Roy is the head of the Department of Engineering Science at the University of Oxford and is a professor of mechanical engineering. Ron has served on numerous society committees, review panels, editorial boards, and is a past editor-in-chief on the of the Acoustic Research Letter, which is called the JASA Express Letters. He's a fellow and former vice president of the Acoustical Society of America and a recipient of the Acoustical Society of America Helmholtz-Rayleigh Interdisciplinary Silver Medal. Ron is an early pioneer in active and passive cavitation detection, both in the context of sonoluminescence and biomedical applications, including cavitation-enhanced heating. I think we all agree that his research forms the foundation for the work presented in this workshop. So our second panelist is Professor Thomas Matula. Professor Matula is a director of the Center for Industrial and Medical Ultrasound at the University of Washington's Applied Physics Laboratories. Tom has been exploring the fundamental physics of cavitation and its use for biomedical and industrial applications, including food processing and fragmenting DNA and chromatin for downstream PCR and next-generation sequencing assays, which this research also led to the formation of a startup company. The Center for Industrial and Medical Ultrasound at the University of Washington, which he currently directs, has over the years made several seminal discoveries related to cavitation inception and its bioeffect, and most notably in direct imaging of bubble vessel interactions and the phenomenon of invagination. So with those introductions, I would like to let me just say a few things about how this panel will work. So we'll have we kind of like thinking of having a conversation about the different topics discussed and those that will emerge. So I would like to strongly encourage our participants to post their questions on the chat window. We would love to have thought-provoking questions. Please feel free to join in that way in the panel, and we will read those questions and we will try to address or facilitate the conversation with the panel. So without further ado, I guess from this morning presentations, I think they were one of the boldest sections was that passive cavitation detection is essential for guiding therapeutic interventions relying on cavitation. But I would like to ask this discussion by kind of like challenging our kind of like, common agreement and notion and the thoughts that have been discussed during the morning about calibration. And I would really like to ask Professor Roy to start the conversation with a question that is like, do we really need calibration?
Okay, so let me first start by pointing out that I'm a big fan of passive cavitation detection, of noise diagnostics in general, because it provides you with useful information. But one of the things that I think about is what Bob Apfel used to always say, which is to understand what it is you're sensing and how it relates to the physical world that's governing the process. And I would argue that when you're talking about noise diagnostics, you're looking at an effect which you're trying to correlate to a desired outcome. And the desired outcome is not necessarily bubble dynamics, it's a therapeutic process or diagnostic process that you're trying to either promote or duplicate or what have you. And the linking between that is complicated. There's a lot of physics there, and that physics isn't always either straightforward or unambiguous. One example of that would be there is more than one way to get a subharmonic emission. You can get it either through a nonlinear response from a radially pulsating bubble, or you can get it from a shape oscillation. In one case, you're going to get a different effect than in the other case, but they both result in subharmonics. Similarly, if you're looking at harmonics in the sound field, that can result from nonlinear responsive bubbles, or it can result from scattering of a nonlinear field from a fixed object, even a rigid sphere or rigid object. So it is ambiguous. And I think one of the things that happens in cavitation is when one thing happens, everything happens. So as a result, you're going to get what you want no matter what. And so I think the key issue here to me is not so much understanding the details of the bubble field in terms of its physics, but understanding that what you're measuring, it correlates to something that you want to see happen, either heating or disruption or what have you. So in that sense, I kind of wonder how important is it that we really make that link, that we can really sort of calibrate things so that we understand that we're having a certain amount of inertial cavitation versus stable cavitation versus something else, rather than just say, look, we're calibrating so that we have an outcome that we can measure that we know is going to correlate to a desired outcome in the body that relates to therapy or diagnostics, and just let it go at that. The other concern I have is that so much of what we measure is going to be system dependent, not just sensor dependent, but it's also going to depend on the environment, whether you have essentially a isotropic medium versus anisotropic, whether you have volume scattering, whether you have rigid objects nearby. All these things will make a difference, whether things are moving or not. And so it seems difficult to me to think of a universal calibration that you can rely on, which would then be applicable across application domains. I would think it'd all be very much domain specific. So I think it's a good thing to aspire to, but I think we're still looking at situations where if you're working in a brain, you're looking at one kind of calibration or one kind of response, or if you're working in liver, it'll be something different. And it'll be difficult to get beyond that, I think.
Professor Thomas, would you like to join? So since you've done also some work in biophysics, and how this could potentially be related to the echoes being recorded.
Yeah, I agree with Ron. In fact, I think it's not an absolute calibration that's needed. It's a relative calibration that depends on the specific application. But I think I want to take it one step further. I'm a user of cavitation. That is, I create cavitation in my lab to ablate tissue for some hopefully therapeutic use. And what I would like to see is I would like to be able to image the cavitation field in real time as a three-dimensional object, color coding the bubbles so that the active ones that are small and oscillating and doing something might be colored red, for example, and the ones that have agglomerated together and are just big marshmallows reflecting sound might be colored blue or something like that. And that way, I can be able to treat my tissue and monitor in real time what's happening. I'll be able to decide when treatment should end. I'll be able to look at what the bubbles are doing, whether they're streaming and things like that. Am I crazy? Is that even needed? That's where I'd like to take this conversation. I'm not sure who to ask.
Sounds like super resolution for cavitation. That's what it sounds like.
Well, there is one notion here that maybe it's kind of like those two approaches. There is also this facilitated by a question that has been posted on the chat, which suggests like, shall we treat cavitation as a threshold phenomena, or on-off essential signal is enough to correlate bioeffects, or we should maybe keep in track all the effects and then adjust their strength as we go along? Or effects means possibly the radiated echoes. What do you think, Elisa, since you jumped in?
Yeah, I mean, I was going to, it's addressed to Ron, this question, but
Sure.
Yeah, so I would say no, because there's so much more in the cavitation than just the binary, information. Definitely, I mean, for us, sustaining stable cavitation for blood-brain barrier opening is important. I try to show how when the bubbles reach the focus, the cavitation is still ramping up. And that has been something that we haven't really looked at, but we can actually look at the perfusion of bubbles, eventually get the concentration of the critical volume to sustain the steady state. I mean, there's so much to do with this signal that, and obviously to image it, that I think just saying it's an on and off and a threshold trivializes to a number. And I think this is just not doing it justice. That's basically based on our experience.
You know, I would agree with Elisa. I think the other thing it's important to look at, which helps with the calibration issue, is what's really useful to monitor is change, how things are changing over time. And a good example of that, for example, we used to do experiments where we generate a cavitation field in either an excised tissue or in a phantom, and we noticed that initially we had a large amount of initial cavitation, and then over time it would go away, sometimes relatively quickly as the temperature goes up. And that's because you cannot sustain initial collapse at elevated temperatures. So you have a method of thermometry that could be exploited that way. So there's a lot of information that you can get just by monitoring changes in the field. And so a threshold is nice to know. It's nice to know when something's happening, especially if you want to avoid it. In the case of not wanting cavitation, but I think if you're going to get it, it's good to monitor what's happening in a reasonably sort of resolved way, spatially, but also resolved in terms of is it inertial, or is it scattering, or is it shape oscillations or whatever. And I think you can get a rough indication of what's happening with that, but from the noise diagnostics and how it evolves over time.
In a distinctly two-dimensional meeting, I'd like to pick on Tom's three-dimensional dream for a second, because I thought there was a very interesting point there. We have heard the talks already in this session, cavitation for both safety and if we think about the first one of those, almost all of the sound fields deploying are three-dimensional. They tend to be a cone of sound that actually reaches the target region. All of the techniques we've heard about today that are deployed in practice are either one-dimensional or, at best, thus far, two-dimensional. Although the cavitation helmet, as I like to call it, that we've seen from Sunnybrook could potentially achieve a significant level of three-dimensionality. How important is it that we be able to quantify and monitor cavitation, not just at the focus, but everywhere in the ultrasound propagation path, everywhere where sound might be getting between the radiator and the patient?
I think it's very important. I mean, for one thing, anything out of the plane of the imaging system is unknown. So if you're treating near a boundary, for example, you really want to know where that boundary is. So maybe part of the answer is in treatment planning. If you know what the target is going to look like ahead of time, maybe then you can just rely on plain imaging of bubbles and leave it at that. But that requires a treatment planning, which is a scan ahead of time, and nothing can change between that time and the time you're treating, et cetera.
Ron, take was to raise his hand, therefore losing.
Well, I'm glad Tom went first, because now I can agree with him. But one thing to point out is that we're looking at field quantities here. So if you're concerned about what's happening in a focus, let's say of a high flux transducer, that's great. But where you're going to measure is going to depend on what's around that focus. For example, if you generate significant bubble activity, let's say from a previous exposure, let's say you form a bubbly lesion, which persists when you move from spot to spot, you'll get scattering from that lesion, and you're going to scatter some of the noise into the aperture of the receiver that you would not have done before if that lesion wasn't there, and that's going to affect your effective sensitivity of that receiver. So you need to be aware of what's there. Probably a real pathological example of this would be what happens if you have too much cavitation in the prefocal area. Then you could be shielding the focus. So you kind of need to know where these bubbles are and what's going on. So I think having a broader field view of what's happening is good. And one way you might be able to facilitate that in a course of treatment is the bubbles that are probably going to matter when it comes to scattering and shielding are going to be larger super resonant bubbles, which are not going to super resonant size, which are not going to collapse inertially, but will produce significant scattering. And that could be detected, let's say, with B-mode ultrasound. You might turn off the sound field and HIFO field and do a quick scan of the region and see if it's generating a lot of hyperacridicity in regions where you don't want them to occur. And that might determine then, for example, that you may want to wait a minute for these bubbles to dissolve before you can proceed with the treatment. And you wouldn't know that if you didn't look for them.
And I think actually off-target imaging is a compelling reason to calibrate, going back to Ron's earlier point, because if you don't, and you've got strong field dependence and depth dependence to the quantities you're measuring, if you leave those biases in there, even if you're watching the treatment, you don't know what they mean in terms of relative values. But more generally, if we think about just trying to demonstrate clinical effectiveness for any treatment, patients vary, and correlation establishment's really hard under the best of circumstances. And if we don't do the things that are possible, and some are harder than others, to try and make the process of correlating activity we observe to a bioeffect we care about or want to avoid, we really just, I think, need to make our job as people who are hoping to get things into a clinic a little bit easier by doing that.
Let me try and combine two of the questions that have come in the chat. One was directed at Ron, saying, are you suggesting that because cavitation is a threshold phenomenon, an on-off signal is enough to correlate with bioeffects? And I think we heard from other panel members that that's not seen as enough, because
no, I don't think so. Yeah.
The second you cross into the on regime, a big on could be very different to a small on in terms of what it does. But one of the other attendees is encouraging us to discuss what benchmarks we should be gearing towards for bubble detection. In other words, if the amount of stuff that happens post-threshold matters, how do we benchmark it across applications, if that's even possible, or even across systems for the same application?
I have a couple comments about, this on-off and some of the discussion that we had so far. I think I would like to differentiate between different types of treatments that might involve bubbles. I think if you're nucleating bubbles and you're trying to maintain them in a controlled way, that's a very complex, problem. If you're injecting preformed bubbles and you want to have a particular bioeffect, there it's just a question more in my mind of dosimetry. If we knew exactly what the dose of the focus was, then we would be, we would have the answer we need, most likely, for the most part. But if you're trying to nucleate bubble clouds and use them as in therapy, I think that's a very different thing. And I think treating things as an on-off, if you're trying to just use, have dosimetry. So we want to know what the pressure amplitude is at the focus, because we know from our animal studies that we need 200 kilopascals to induce blood-brain barrier opening. Then you could say, okay, well, when I see the onset of a big spike in subharmonic or harmonic emission, that's an internal calibration. So I think there are different ways to look at this, and it's depending on different ways of using bubbles.
Thank you, Nathan. Other thoughts on the benchmark?
I like to say that in terms of as far as passive cavitation detection pipeline or systems are concerned, I would be delighted if in every section of a paper, for example, somebody reports the sensitivity of the system. So let's say if you are recording harmonics in 1 megahertz, it will be quite useful for everybody to know what was the sensitivity of that system in terms of millivolts per Pascal or Pascal per millivolts, if you like. So everybody knows, for example, when somebody says, I reached the level reporting ultraharmonics, for example, reporting subharmonics, which can be associated with the physics, we know that this level can be compared with another lab that probably did not record or record them at a much lower pressure. So I think being able to know how sensitive every system was might be very valuable in terms of eventually really identifying the bio effect and coming up with ways to quantify, not in absolute terms, but at least in terms of across different labs and institutions and systems.
Kostas, do you mean the sensitivity of the receiver?
Yes, of the receiver.
Or the receiving process? Because if you have a focused receiver, are we talking about pascals in the focus per millivolt out of the receiver? Because then that might depend on the intervening propagation path, because the presence of scatters and so on and so forth. It might be difficult to have a single metric for that.
But at least
you can always calibrate the receiver directly.
We should at least publish value measurements in water, like we do with the source. We should say that in the focal region, you could provide a sensitivity map, that was in absolute values at a specific frequency that you're using for your experiment. Then at least people could compare from site to site the whole system. So you would involve all of the filtration amplification, but you would want to publish what the sensitivity is for a source at the focus is on your detector.
But what if that changes depending on your medium? Wouldn't people get the wrong impression?
No, but at least we'd have a baseline of the equipment. I mean, we do the same thing when we apply, I'm saying that we estimate that it was a megapascal to focus when I applied this ultrasound into the liver. And we don't really know what it is, but we still need to report some standard of what the value was in water. I mean,
I just think the sonic chemistry literature where they do this sort of thing and people just apply these numbers without thinking necessarily. I think if you're careful about understanding what the sensitivity means, then that's a good thing. But otherwise, it could be misleading. So I would add a caveat. This is what the sensitivity is in water. Be aware that it could be different in liver or bone or whatever it is you're working in.
I mean, I think that's quite clear from today's presentation. And whoever joins now our panel, I strongly encourage them to attend the presentation that really nicely discuss all the points that Ron brought up. But at the very least, will provide some reference for a given application. Right. So I do agree with what the comments that you mentioned, your points, Ron, about different applications, different environments will be different. But if we go, for example, for the liver, I think it will be quite interesting for people that work in the specific problem, at least being able to reach to a consent about whether the signals they detected were kind of comparable, or if one lab reports signals and the other lab says we didn't even see ultraharmonics in our experiments, and we still have the same effect, right? So at least we will kind of provide some consent moving forward.
I definitely agree with that, and I thought Mike covered some of the medium-dependent attenuation effects and the understanding of the transfer function in his talk very well. But as a starting point, you need to know how two detectors perform relative to each other in water. The other idea I'd like to invite the panel to discuss was one that was brought in by one of the early questions from an attendee, which is characterizing a detector really is a job for more expert groups. It's actually quite difficult to calibrate a PCD on receive. What about this idea of a standardized source of a point transmitter that would have one or two or three methods of transmission that even less expert labs could put in front of their PCD, both in water and potentially in the tissue that they use ultimately, as a method of standardizing or displaying a standard response. And I'd love to hear from everyone, but I'd also like to hear from someone like Kyle on the feasibility of manufacturing a standard point transmitter with enough tightness to be usefully deployed across laboratories.
Yeah, so go ahead.
So go ahead. Sorry.
Yeah, a couple things. I mean, we haven't done this, but I've been reading about, just using a pulse echo and comparing that pulse echo calibration versus a pulse catch. So that negates the purpose of, if you use pulse echo, it negates the purpose of the source. But yeah, there's a couple of things to this. So we've sold, hundreds of these Y107s to researchers. This is a little bit outside of your question, but a handful of them have asked, well, what's the frequency dependence on the curvature? So people are using these. They don't really understand what's going on. They just are looking for some feedback in the harmonic content, but there's no appreciation of the curvature, the medium in which they're using it in. So, the Y107 to me is a good baseline. If I had all the time in the world, I would take that information and all the publications, and I would try to just, see, kind of develop a matrix based off of what everybody's using it for, and, get a sense of some sort of baseline for different indications. But, the focusing attributes and the attenuation and patient differentiation is a huge issue. But anyways, to answer your question on a source transducer, yeah, that would work. I should send along a paper I just read, though, that you get a lot better spatial averaging across the aperture using the pulse echo concept, and that's in free field. But again, that all goes away when you have this frequency dependence where the amplitude changes with respect to the axial distance and the attenuation and the impedance path in which it's used for.
Almost all of us work in the frequency range 100 kilohertz to 1 megahertz, and almost everything that we detect is never any higher than 2.5 or 3 megahertz, even for deep abdominal applications. So a broadband source that could produce a signal between 100 kilohertz and 3 megahertz with a hugely consistent way, and could be deemed to be a point transmitter across all of these frequencies, would go a long way. I'd love to hear from others here in terms, particularly.
Do you want a solution? You want a solution? We've done this before. You take an absorbing sphere, put it in a non-diffusive medium, either a gel or liquid, optically absorbing sphere. Take an Nd:YAG laser, hit it with a 5 nanosecond pulse. You'll get a broadband acoustic emission, which is going to be an outgoing spherical wave that's very reproducible and very easily characterized. And you vary the size of that sphere, and you can vary the center frequency of that emission. So if all you want is a point source, you can do it that way quite easily.
Well, that's a great suggestion. Can anyone make that so that it doesn't require a big-sized optics room to run it?
Oh, you could do it in a paint can. You don't have to be in an optics room. It wouldn't be that difficult. Tom does photoacoustics. He knows how to do this.
We also have, intentionally invited many people from industry, and we also heard today from Kyle and others. So we really want to. We don't want to. It's not the ideal for labs being able to retain very specific equipment, but if the labs have expertise, maybe that will be a good way moving forward, joining with industry and making products that will be useful for everybody.
I'm happy to develop something with some of your expertise and call that the golden standard. That's something. I think what we're missing is, like you're saying, a source transducer, or just, a piece of equipment that's standard for characterizing any type of PCD.
Even the source transducer, though, would be required to be calibrated or tested periodically to make sure it's staying, nominally functional.
Sure. Yeah. And within the general practices yearly of checking that sources would be, that's conventional. But yeah, I think you guys are right. We need to standardize the way in which we do it if we all feel like that's needed.
Or you could try to make it low cost enough that it's a single-use disposable that effectively comes calibrated, and then you use it once. And I think there'll be another tantalizing possibility. It's almost like, the acoustic equivalent of your pH strip.
I would also learn something from imaging, which is basically the phantoms, right? So when you get a new scanner, you get a new transducer, you have a phantom that's AIUM approved, and basically you check your resolution, you check your intensity, your contrast, all that's important in imaging. We can have something equivalent of a flow phantom that's also used for Doppler, for example, and then we can run, bubbles through it. There are a small pump, a fusion pump that runs to the phantom. And then I think this is a little bit better than just water, right? Because we know things break in vivo and also ex vivo. When you hear attenuation, you have all kinds of scattering and that you may, or other vessels that are in the path with bubbles or without. So that we can work with the manufacturer that does phantoms. I mean, there's few of them, AIUM approved again, and we can just work also on a way to do the flow and have something standardized.
I'd maybe like to add on that. I mean, I like the idea, of course, of a nice perfect point sphere, and that has, that's appealing to the physicist in me. I like Elisa's idea, though. I mean, if you developed a phantom, right, that you would flow a known set of microbubbles through it, a commercially set of microbubbles through at a particular dose. It's got a transducer that's affixed onto it that creates, ultrasound, and maybe it's a broadband one, so you could tune it, but it's calibrated, and then actually be able to produce cavitation. Now, of course, any one incident, it's stochastic, it's going to vary, but if you collect, 100 or 500 or whatever averages across that with your PCD, now you can really start to get something, I think, that's more akin to what we want with cavitation, right? So it takes into account the fact that you've got an ensemble of scatterers and not just a single point source. And I can see value, of course, in either of those.
Yeah, I agree. And this also might better address the point that has been brought up by Ron on respect to different applications, different objects, different organs might be able to produce completely different results. So having phantoms that will allow us to potentially calibrate the sources for different organs or applications, it will be I think, enormously useful.
And for the brain, I think it's important to include the skull. Most of the time we just think it's the thickness, as I mentioned a little bit, but it's also the curvature. And Konstantin brought the idea of the 3D, but if you're hitting from different incidence angles and you're getting different side lobes and different regions, the 3D adds so much complexity unless you have calibrated with a skull phantom, as we all know, working on the brain. There's no way you can do anything with an array. You can get away with a single element, but not with multi-element.
Yeah, I would agree with that. When we do ablation studies, the energy we need to get to an ablative temperature varies by an order of magnitude between patients, and we're sonicating the same target each time. And so far with BBB, it varies by a factor of 5. So I think it's a very challenging calibration. If you want to have some sort of measurement of it, not just something is happening, but what the magnitude of it is challenging.
There's another question in the Q&A I think is worth turning our attention to. So this was raised earlier and it's been raised again about the concept of a gold standard. There's 2 questions, and one about sharing scripts, details of implementation of the signal processing methods for non-expert users. Is this something that panelists think is doable, necessary? Could we create a library with a specific transducer, a specific preamp, a specific data analysis code in MATLAB and LabVIEW that we would be happy everyone to be reporting against? Please discuss.
I know I suggested something akin to that in my talk, so I'll take a first stab. Which is, I think, to say first, we need to follow the example that Mike provided, right, of breaking down the system, right? He talked about the electroacoustic, and then he talked about the the tissue propagation path. I think here what we might consider is breaking down a third step, that you have a, for lack of a better phrase, a hardware electroacoustic, right, and then you've got a signal processing component to that. Right, the signal processing part, I think, is very doable, very easy to incorporate, and I think we absolutely should be doing that. I think from a hardware perspective, I think it's doable now. Getting it out there for every single system is going to be hard, right? Because there's so many different iterations of it. But as Kyle mentioned, right, there's a lot of Y107s out there, right? So doing it for some of the most common ones is I think, quite doable.
Any other thoughts on general researcher and research leader willingness to create such a library and also its usefulness?
I think this library will be, I don't know what will be the reason for that library, but I think being able to somehow collect data, at the time that we are right now, that, with many tools and methods to analyze big data, this might provide several, might allow to create a database that we might also do some data mining and identify signatures that could be associated with a bioeffect, in addition to potentially creating a baseline or a reference for everybody else to try to at least comply with, or being able to incorporate in their setup specific signatures.
Okay.
I wanted to make a comment. I think it's, for research purposes, the curved array and the large aperture is great because the signal to noise ratio is really good, and you're confocal, you're at the bubble cloud. From a clinical aspect, so calibrating a focused source is really difficult because of the phase distribution. You get rid of the phase distribution, the smaller the element is, to get the near field, far field closer to the element. If you just had a bunch of small elements, kind of like what you were alluding to before, Costas, where you have multiple elements, but they're diffracting at a certain point, it makes calibrating a lot easier in a clinical, and so just for safety and efficacy, you can negate the phase issue. I'm just wondering if there's a play there, getting rid of the curved PCDs for clinical use and dealing with, manageable PCDs that, similar to hydrophones, hydrophones are calibrated 1 meter away to make sure they're in the far field. So giving it a similar chance of knowing that the phase issue is not there. Just food for thought.
Yeah, I think to follow along that Kyle's point, some of this is going to be about helping especially newer researchers in this field understand how to make hardware choices. There are some things that just are really well suited, for example, for B mode, that aren't well suited for passive cavitation imaging. And I think being able to make some recommendations from folks who have been working through these problems for a while already, what to pursue and what to probably avoid, I think would also be helpful, along with a code repository.
Thank you. So I think we seem to have some consensus, at least amongst the panel, that there is a need for a level of calibration that simply on-off, or knowing when something changes on its own, will not cut it. That there are challenges that would make that calibration extremely application specific, and that therefore we need to find a way to make that easier for the non-expert users, by potentially using either a calibrated source or some other methodology in the form of a library that would then make it possible for people to compare the sensitivity of the detectors across laboratories. One of the other points that has been raised on the chat, which I think is interesting, bring into here is there any way whereby something could be acquired in patients, now turning to the more clinical applications, with or without bubbles, or before bubbles are infused, or before cavitation is generated, in order to provide some sort of standardized metric by using the patient as their own control, in other words? And is that something that particularly the people who have worked clinically have come across and have considered as a way of establishing the sensitivity of the detectors and therefore the cavitation measurements?
So I can quickly address that. So when we do both preclinical and clinical, especially preclinical, we inject saline, and that establishes, the noise floor, if you will, or cavitation happening without bubbles for us. And then from that floor is where, after we inject the bubbles, you will deviate from that. So we definitely, us and others, I'm talking about our group, we definitely use that as first of all, is a detector picking up the difference after injection, IV in this case, and then whether we're able to establish the noise floor from spontaneous cavitations and not bubble related. So that could help, and that's something that we really strong believers for establishing beforehand.
So I guess this approach, which I think we all use or have used in some way or another, really depends on how credible the unnucleated environment is as a benchmark. So you talked, for example, Elisa, about injecting saline or administering saline. Well, I can tell you from very candid experiences in my lab that depending on who's doing the saline injection, your likelihood of entraining air or not entraining air is highly variable. So to what extent do we think we could find a way that doesn't involve anything that isn't so heavily impacted by user and environmental factors, and other user and environmental factors that should be considered?
All right. Well, so it's a manual injection. And unless you, of course, use a pump, and if you use a pump and it's an infusion, then you definitely have a higher chance of getting a more, repeatable, calibration there. But if you do manual injection like we do, and I know that some of the people here are not doing that, then that depends a lot on who is actually injecting, how fast. When are they doing the flush? All that stuff is something that I think with the cavitation and saline, you can pick up. Provided, of course, you have the right sensitivity. But I think it's something that it does provide a self-calibrated system at every injection. And I think it's a feedback that you can use, as opposed to just assuming that everybody pump or no pump will have exactly the same thing. You always have to obviously double check and triple check that the assumption of standardized is there, right?
So in the absence of a calibrated system, what conclusion would we draw if group X reported seeing no cavitation in the native brain at 1 megapascal, and group Y said, we don't see any cavitation in the brain at 1.4 megapascals, unnucleated?
Well, it would depend on the frequency. Hopefully they're reporting that.
Assuming they had used the same frequency. Nice, but that's too easy of a get out of jail free card. Let's assume they had used the same.
I don't know. I just want to mention that, we all have come up to this kind of dilemma, how to reference our data. And I think acoustics decibels, it's always like a unit that is being used, across different disciplines. And we all know, or some of us know, that decibels is all about where you reference it, right? So it's a non-unit. So the reference for that is quite important. While in one case we said referencing that to kind of calibrate point source. In kind of when you do the experiments, when we're doing experiments, both when I was at Brigham with Nathan and now we're doing in the labs here, and I think Elisa is also alluded to that. I think recording data before the onset of bubbles or below the point that we think, if we have microbubbles, it's very easy because you just get data before you inject the microbubbles. If you want to induce instantaneous in endogenous cavitation, you just have to go to pressure just below that threshold and record sufficient waveforms, right? So you can use that as a reference. So I think that can provide some sense of self-calibration. It doesn't address the issue of sensitivity, whether somebody reports something versus not. It's all about sensitivity, but it does provide at least something that we have discussed, the strength, right, with respect to baseline. So that can be quite useful in many ways.
Just, I want to rephrase because I didn't answer Constantine's question. So when you have a 1 megapascal and you're at 250 kilohertz and you're getting a flat line in non-nucleated saline, and then you report a sensitivity that's high, then there's something obviously that doesn't check in your application. Now, if you're in the brain, there could be, you add an incidence that with the skull that you will never hope to get anything back to your PCD or your detector. So I think a lot of we can definitely standardize that a little bit and say, there's, if you have a specific collection of parameters, like whatever it is, pressure, frequency, duty cycle, pulse length, right? And you use that concentration of bubbles or that concentration of saline and you inject in your animal, depending on which organ you're going after, you should be able to get an elevation of your cavitation signal. And if you don't, check this, 1, 2, 3. So we can do a manual like that. I'll be happy to contribute to that because we've done so much of. I think we kind of know now that there is a range where things should work, at least in the brain. I don't know about the other organs.
Very interesting thoughts. Almost like a library of verified calibration experiments that use some sort of known transmitter, some sort of known or standard receiver, some sort of standard microbubble at a known concentration, and tell people you should be seeing something happening in that range.
Exactly, and this goes back to the non-physicists or engineers that want to jump into this. We, as all of us, we're mentoring neuroscientists, neurosurgeons to basically work on that. And I know Kyle is also selling some systems to these people, so maybe he can say something about what is the manual that you're sending them to be able to say, hey, our system in your hand should work if you do this right.
Okay, so no news is good news for us. So we do correlate our electrical impedance from dry to wet based off of simulation. That's how we say, based off of a certificate of analysis, it's performing based off of what we designed it for. It should have this K value at the surface. Because of the axial focusing attributes, we just give a certificate of analysis based off of the radiating surface. It's not calibrated, but it gives them the assurance that we did our job and that it's about to that sensitivity that we claim it is. With the cable, if they plug it into a mega ohm oscilloscope, that's as far as we go. We don't do any free field calibration or anything because of those frequency dependent issues we're talking about. And I'm open to suggestions, of course, but people are publishing results because it's so sensitive. I just don't, I don't know the uncertainty associated with those, obviously.
Constantine, are you kind of referring to having a way of having a sanity check so a person can check that their system's actually working, whereby they're looking at an expected result, and if they don't get that result, then there's a problem? Is that kind of where you're coming from here?
Well, it's not where I'm coming from. It's actually where some of the questions in the chat have been coming from.
The only thing concerned, if we're going to do that, for example, you could put a fluid in a tube that has no bubbles, and you could argue that there should not be any cavitation. So therefore, if you see a signal, you get a problem. or you might increase your pressure to a level that you expect to get cavitation. If you don't see a signal, you get a problem. But I think if we do that, we need to impress upon the fact that they need to be careful what that fluid is and how it's processed. And you mentioned, for example, manual injection versus mechanical injection makes a difference, but also just the temperature of the fluid, the dissolved gas concentration of the fluid, all these things make a difference. Whether you're a lot of neutrons in the environment make a difference. So these are all things that people need to be aware of if we're going to use that as any kind of standard as to whether you should expect to get or not to get cavitation.
I wasn't so much suggesting it as an in vitro standard, because I think in vitro we can do better things. I was basing it on the fact that not all humans come naturally degassed.
Well, most of us don't have very many nuclei, depending on the organ. Some organs are replete with nuclei, but
and the fact that most of us, when we have performed repeatedly measurements in a particular medium, be it the brain or be it the liver, actually manage to achieve some sort of consistency across individuals, because biologically things don't vary as much as perhaps we collectively think they do. So it was more about, is there something in a situation where you cannot put a calibrated point transmitter or a tube filled with a known concentration of bubbles in front of your PCD, i.e. when you're treating a patient, is there an alternative approach that might actually yield a reasonableness of measurement certainty?
Mm-hmm. I can tell you what we do for sanity checks before each experiment is I put a bottle of Perrier at the focus and run a mock experiment. And in the brain, the emissions are very similar to what we get with microbubbles. So.
I will just say that that's madness, because Perrier, c'est fou. I couldn't help myself.
Maybe a good consensus here as a manufacturer of these things. In the background, speaking of source transducers, we do use our H101, which is 1.1 megahertz. We plug in the Y107 and we put a polypropylene ball at the focus. And we just want to verify that the amplitude is right and at that frequency. I'm wondering if you guys think that I should go a step further and making the H101 a source transducer for all these Y107s and do one at 1.1 and 3.3 at the third harmonic to give you in the certificate of analysis to baseline. At least we know that correlates to the radiating surface. It's nothing to do with bubbles. It just gives people an idea of unit to unit for when they're delivered to one university. They can claim, we were about 10% off compared to this other university. Do you guys think that's a relevant measurement for us to do for every PCD we sell with that source in-house?
It's interesting. It's similar to what Panametrics used to do, maybe still do, with their single element transducers to characterize them. They would take a target sphere and they would measure the impulse response by looking at a mass scatter from a target sphere. And they would use that. Every transducer they would sell, they had that particular impulse response and a frequency response, and provided with the transducer so you could essentially monitor the health of your transducer over time. But it's just similar to what you're suggesting. But
it's just what frequencies would we agree that's relevant? I'm not,
I can also comment that the frequency, I agree that's important, but also we shouldn't forget that, the transducer, as soon as you deploy the transducer, you send the transducer to labs and companies, the remaining setup, preamplifier and readout will also be quite important. So any calibration, I think, should happen on the recorded data of the system. That includes all the other components that are essential for digitizing the data.
Yeah, but the curved PCDs don't need a preamplifier. There's no reason for it. It's got too much sensitivity just into a calibrated oscilloscope. If they're using a calibrated oscilloscope, and if I'm able to give them two points along the frequency spectrum, they have their baseline.
Well, this is kind of what I was angling for, which is I wasn't even thinking of you using a transducer, Kyle. I was thinking of you using your kind of Y series hydrophones, not as point receivers, but as point transmitters, and actually driving them to create either a signal that is reminiscent of broadband or a signal that is reminiscent of certain narrowband emissions.
Yeah.
And to Kostas's point, you would always have to worry about your downstream receiver path.
Yep.
But you would conduct the test by actually plugging your PCD directly into a digitizer for the purpose of this test in order to report it. Then you'd worry about everything else downstream separately, but at least it would tell you that, yeah, the cavitation detector you're using a standardized source, is capable of detecting acoustically what you want it to be capable of detecting.
Right, that's a sanity check rather than like they give you the ability to compare across different labs, because impedance mismatches will be there depending on what cable you will use. Gain and amplification will be different depending on what's the signal, what's the gain of the amplifier. So all those will save your signal to some extent, I think.
But then you could repeat the measurement with a complete signal acquisition path in place, and then you're now suddenly getting to something which you can compare across setups. So
I think you have to rely on a certain amount of competence from people who use these products. I mean, if you specify the end of cable sensitivity, let's say, into a known impedance, let's say 50 ohms, that should be enough.
Yeah.
You know, all these scopes have that termination, and at that point, if a person wants to throw in a preamp or whatever, a filter, then it's up to them to figure out what's going on.
Yeah, extra cable, whatever it is.
Yeah.
By the way, don't use 50 ohms because already almost the entire research community has moved to these picoscopes and these DAC cards, and none of them have 50 ohm terminations. How would you doing 1 mega ohm? So if you really want to make it ubiquitous, do it into high impedance. I know.
It depends on the length of the cable and the frequency you're working at. If you're working on very high frequencies, you want to be careful about the impedance of your cable relative to the impedance of the load. And a lot of, like Audio 58 is a 50 ohm cable, I believe. That's the only reason I mentioned that. And you can always just put a 50 ohm shunt terminator and deal with it that way.
The problem with a source, at the focus, of a curved element is going to be that you have side lobes that, we need to consider. I mean, this will only be at one point. So how do we mitigate that false side lobe, and do we care about it? It's probably 3 dB down, at higher frequencies, you say up to 3 megahertz, but down at 0.25, your side lobes are all over the place. How do you calibrate that out? To that point, it won't work. People are just going to get false readings at these lower frequencies.
Oh, well, solving that is what we have you for here, Kyle.
We could axially scan at 1 millimeter increments, I guess, and take data that way. That's one way to do it. Just that's an interesting thing.
That's what I would do. I mean, if you have a calibrated point source, if such a thing can be made, then it would just be like a hydrophone scan, but in reverse. So you transmit with the hydrophone, receive with your detector, and then you would report the peak sensitivity, and you could either show a graph, or you could say that there's just, it's the width and the length, just like we do on the transmit side.
Yeah. Yeah. I mean, if we negate the phase issues, that's definitely reasonable.
Maybe this is a dumb question, but if you're transmitting with a point source and your detector is stationary, wouldn't that all be taken into account in that scan? If it's off axis, it would be reduced sensitivity for that reason, right?
Yeah.
If it's small, yes.
We're nearing the end of our time, so I think I would like to maybe give everyone the chance to give one or two final closing sentences, and I'd like to start with our non-panelists. So I'll finish with Tom and Ron. So maybe Elisa, if I start with you, just a couple of sentences on what you've heard today and what thoughts it's generated, which could also continue into the subsequent sessions. We don't need to arrive at any definitive conclusions today.
I I think we're in the right path to create something more standardized, and I think we can definitely make it easier for other people to also use cavitation detection, and I think that would be great through this workshop at the end to maybe put this something of a manual together, or library, or whatever you call it, or even a phantom like what Brian suggested in the chat, that with the contrast enhanced imaging, contrast enhanced ultrasound has done a lot on that front, and we can piggyback on that. So I think overall there's a lot to do, and we can all help to make it more amenable to others.
Thank you very much, Elisa. Nathan, would you like to go next?
Yeah, I really appreciate this discussion, and I think we need to continue it. I think going forward, it may be useful to look at, for focused ultrasound neuromodulation, there's something called iTrust that have been tackling these sorts of questions for that application. And they have a number of working groups, and they're looking to create these sort of standards. And they're also looking at having standard simulations so that people do transcranial simulations of a specific set, and then they can compare theirs to the standard. So I think a lot of the stuff we're talking about today is very important, and we should continue it, and maybe we should look at that effort to go forward.
Thank you. Kevin?
So I'll mention a couple of things really quick. I like the idea of coming up with something simple that can be deployed in labs that are not experts in these areas. I also like the idea, though, of labs with great expertise in this area working together to kind of identify what those limitations are, and getting those limitations of these kind of simplified systems out there. And I know we've mentioned this phase component quite a bit, so I'll just use this as the pitch, right? One way around that is to use small receivers, which means we have arrays, which everybody should tune in next week, because that's what next week's going to be all about.
Thank you very much, Kevin. Kyle, any parting thoughts from you?
No, this has been really insightful, and I think that Nathan's suggestion, the iTrust for neuromodulation, that works, and I'm in the equipment category there, and I'm talking to all the competitors, and we're all motivated to create a standard in which to define this stuff, and so it's working. And, it gets outside of it. We're all agnostic. Let's move the field forward and get everybody in the same room. I'm an advocate for that.
Thank you very much indeed. Mike, I'm not sure I've given you the chance to speak yet.
Sure. Well, I hope Kyle or anybody else who is working on these devices is able to succeed. I'm aware of some prior attempts by other organizations to come up with point-like broadband sources, and they were neither point-like nor broadband, and highly directive, as it turned out. It's a hard thing to do, especially if the end user is interested in doing broadband monitoring. Getting that bandwidth out of a single transducer is not trivial. And just taking another lesson again from somewhere else in radiology. So in PET, they use dose calibrators. And the idea is that what's coming out of some source in some medium. And by the time it's gone through the path, the devices, the processing, you should get a standardized number at the end of it. And I think working towards that kind of start to finish approach in this would be a good way to help bring some of these numbers together, bring some of the error bars down in trying to come up with correlations between exposure and what we monitor and bioeffects that we are interested in.
Thank you. Kostas, would you like to share any thoughts?
Sure. I think there is I really like the statements. If you do cavitation therapy, you definitely need passive cavitation detection. So I think passive cavitation detection should be considered, continue being the gold standard for monitoring and guiding treatments that include cavitation. We need to have some point sources that will allow us to reference our signals. And essentially, I'm summarizing what has been discussed. Phantoms could be extraordinarily useful, especially with respect to adjusting these measurements for different applications. And we need to identify ways that will allow us to have some self-calibration, some basis when we apply those to patients. We probably try to use some signals that are emerged while we're doing the treatment patients, which will allow us to level the reported acoustic emissions. And yeah, I think those are like great points, and I'm really happy that there is a consensus in that direction. And yeah, I think it will be great to move those forward.
Thank you very much, Kostas. So now to our two panelists. So Tom, would you like to give us your thoughts, and then Ron will go next and last.
Yeah, thank you, Konstantin. It's been a great start to this workshop. And I think that this workshop can help us do one important thing: gather our thoughts together for determining a program that could be funded, say, by the NIH, that would lead to a calibrated system and that everybody could use throughout the world. But I think we all muddle through this ourselves in our own labs, and we come up with our own solutions. And this workshop is a great way to kind of coalesce our ideas into what we could have maybe as a big program.
Thank you very much, Tom. And then Ron, please, over to you for closing statements overall.
Well, one of the things that occurs to me listening to the conversation is that there's a desire to come up with common tools that people can apply in a relatively uniform fashion. And I think as long as we're working with the body and working with in non-homogeneous, heterogeneous media, it's going to be difficult to really make that work across the board without really raising awareness of what the limitations are of these tools. And so it's, I think a big part of this is going to be coming up with a way of educating people to make sure they understand, well, when I come up with a number of sensitivity for this transducer, this is what it really means. It means this is a sensitivity I measured in water. Be aware that it may not be the same in your experiment, and you need to know why. So one of the things we did about a long time ago, maybe 40 years ago, I was a part of a working group with the Acoustical Society where we tried to put together a set of standards for cavitation detection and monitoring. And it was an interesting experience. It was a working group chaired by Wes Nyborg, and we met for about 5 years, twice a year, and we pretty much got nowhere, frankly, because we couldn't even come to terms on what a definition of a bubble was. Charlie Church was part of that group, and he kept on changing the definition of a bubble, it seemed, every time we met. And so we finally decided that it was too early to have a standard because we couldn't come up with a framework by which we could hang a set of expectations that a standard would address. And part of the problem is we were too broad. We had people working in ocean acoustics, people working in industrial ultrasound, medical ultrasound, physical acoustics, and they all had different perspectives. So it was just too broad. But now I think things are beginning to coalesce a little bit. And I hear today a number of people with common concerns and common desires in terms of what outcomes they want to get from this engineering and science. And maybe the time has come to revisit the notion of maybe a standard for cavitation detection and monitoring in a limited scope. And so maybe, Brian, maybe it would be worthwhile to thinking in terms of getting the AIUM together with the ASA to revisit this notion and put together a document where people can rely upon that not only provides guidance for how to make a measurement, how to calibrate what the options are, but also what that measurement really means when you go to apply it in a messy situation like a sonochemical reactor or a human brain.
Very much, Ron. So we hope very much to be able to produce at least a starting version to that document at the end of this series of workshops, and we strongly encourage everyone who wants to be involved and is currently listening in to raise their hand and be so. We will keep revisiting these questions in the next 5 or 6 workshops throughout the panel discussions. I'd really like to thank everyone for giving up their Friday morning or the Friday afternoon or their Friday or some version of their Friday, depending on where you are, to be here with us. And would like to pass the mic back to Brian and Fred in case they have any closing statements. Thank you all very, very much.
Thank you, Konstantin. Thank you, Kostas.
Thank you.
I think our session is complete. Thank you all for your time. Have a very, very good weekend. And see you next Friday.
Fred, did you have an announcement for upcoming events?
Yeah, thanks everybody. I mean, thanks speakers, panelists, moderators, attendees for these questions and very exciting discussions. Just to remind you that we will be meeting again next week, same time, same place, to discuss cavitation, localization, and mapping. And to remind you that the recording of today's session should be available early next week. Thanks again, and see you next week.